Те трябва с камера. Да, част, не става въпрос нещо да ви се Sorry, we are waiting for Nelly Koseva from the Academy, and in 2 minutes she will be here, and we will start. Okay, we are ready to start. So Verichka prepared some text, and I will read it because she has some flu, or we don't know what, but high temperature, and she is not able to come. Very sorry about that. So, dear guests, dear colleagues, it's a pleasure and great honor for me, on behalf of the Managing Board of the International Center for Mathematical Sciences, Sofia, to welcome you in the Institute of Mathematics and Informatics at the Bulgarian Academy of Sciences on this nice occasion, the opening of the conference Women in Mathematics of Southeastern Europe 2023. The initiative Women in Mathematics of Southeast Europe started in December 2020, when the inaugural conference took place. The main goal of this initiative is to promote the role of the female mathematicians, to disseminate new results, and to create new long-term collaborations among scientists in Southeastern Europe. A special distinguished guest of the inaugural conference was Professor Mina Taichar from the Bar-Olam University in Israel and the University of Miami. She is the director of the Emily Noether Institute for Mathematics and the person who is leading the multi-year program on advancing women in mathematics across the Americas in the University of Miami. She is the chair of the scientific committee of our conference, including also Professor Philip Griffiths and Professor Lyudmila Katsarova. Now I would like to give the floor to the director of the Institute of Mathematics and Informatics at the Bulgarian Academy of Sciences, Professor Peter Boyman. Please, Peter.
Thank you. It's my great pleasure and great honor to welcome you in the Institute, the conference. And this conference, this edition, and with its idea to underline the role of women in mathematics, and especially in research in mathematics, comes in its edition as a steady and developing event. And some of you are here for second, maybe even for third time. Some of you work here, so we are proud with all of you to participate in our conference and to help us to move it further. I would like to thank to the organizers. Special thanks to those which are on the other side of the ocean for their energy, for their work to have the conference. And I believe that they will continue the same way. Of course, the most important thanks are for the participants they make the conference, and I believe that you'll have a nice, fruitful conference with interesting talks and more interesting conversation in coffee breaks and other events around. So let us wish good luck for the conference and everything the best, not only in the conference, everywhere.
As I mentioned, we started this initiative, Women in Mathematics in Southeastern Europe, inspired by the ideas and the great enthusiasm of Mina Teicher. And we are organizing this conference in collaboration with our partners, the Institute of the Mathematical Sciences of the Americas. It's my great pleasure to give the floor of Zoom to Professor Mina Teicher, the chair of the scientific committee, who made the effort to wake up at 6:30 in the morning to welcome us from Miami. Okay, please, Mina, you have the floor. Please. We cannot hear you. I don't know.
Is this the maximum?
I'm not sure. Yeah, but in the room we cannot hear.
This is the fourth time that this is taking place, and it already became a fixed point in not only Southeast Europe, but even further dimensions, and it has a great influence on the terranean, on the area of mathematics, and gives so much visibility to the great women scientists, that mathematicians that are living in this area. The speakers are amazing, but also the organization is very good. I wish I would be able to be there in person, but I am going to follow your lectures anyhow on the internet or by Zoom. But I wish you a very good conference. This is a possibility to meet, for you to meet in person. We create new collaborations. We know how conferences are being a catalyst for new collaboration. And it might be a good opportunity also to congratulate the Center for all the beautiful conferences and scientific activities that are being held. The people come from all over the world, but in this particular case, this is really very unique. Not because because it's the continuity, because you can count on it, because it's already the fourth year that this conference is taking place. And I'm happy also, of course, to see the scientific director that is here, and to congratulate him on the programs that the center is holding. And of course, I'm also happy for the collaboration with the University of Miami and the program of WIMSA, Advanced in Mathematics across the Americas, and Bulgaria is the first one outside of the conference, and thank you very much for all the organization that was done. And I'm sorry that the deputy director is sick and cannot be there, but she did everything by internet, so everything is fine. Thank you very much.
Okay, thank you. We are honored to have here also Professor Nelly Kosever, Scientific Secretary General of the Bulgarian Academy of Sciences, who will congratulate us on behalf of the governing body of the Academy. Please, Professor Kosever.
Thank you for the word, dear organizers, dear colleagues, dear participants. It's a great honor and pleasure for me to greet you with this very interesting and very important event. On behalf of Academician Rivalski, who is the president of the Bulgarian Academy of Sciences, and of course from me, I would like to say that I believe that this important event that is organized by the International Center for Mathematical Studies of the Bulgarian Academy of Sciences and the Institute of the Mathematical Sciences of the Americas at the University of Miami will stand as a platform for inspiration and collaboration in the field of mathematics. I'm sure that the conference will provide not only a floor for sharing the achievements of women in mathematics, but also to foster an environment of inclusivity, support and empowerment within this very, very vital scientific discipline. So I'm not a mathematician, I'm a chemist, and
Very close.
Very close, and we have studied a lot of mathematics at the university and still using a lot. But when we're thinking about sciences, for chemistry is said that it has its central role among different scientific fields. But for mathematics, we can say that it has a fundamental role, and it provides this universal language that transcends boundaries, cultures, and genders. And it is foundation upon which our scientific understanding of the world is built, because it is just the horizontal tools that cross all disciplines. Presently, we have, this procedure for financing of new projects within our national plan of resilience and recovery. And I can assure you that there are very interesting projects that are cooperation between social and mathematical sciences. And it is a great pleasure to see these interactions between scientists, sciences, and of course providing really new perspectives for development of our joint projects and of course our advancement in society as a whole. So the Bulgarian Academy of Sciences is committed to support the initiatives that promote gender equality and the advancement of women in all fields of science, particularly in mathematics. Especially natural sciences are attracting more and more women. And just to share one more thing, I was very happy when in spring I have been contacted by the Bulgarian embassy in Japan, where some Japanese ladies that have a very high managerial positions at Mitsubishi company, they wanted from us to share our experience about how women in Bulgaria are motivated to do research, to work in scientific organizations, to carry the burden of being project leaders and so on. And it was a really very interesting event to see how people from more or less very technologically developed country would like from us to share our inspiration for science and doing research. So I would like to extend my heartfelt gratitude to all organizers, speakers and participants who have made this event possible. And the forum is a place where discussions and collaborations will inspire new ideas, discoveries and innovations. I really deeply respect your dedication and passion for mathematics as a drive for the development of all sectors of activities, not only science. In closing, I would like to wish you all a highly productive and enlightening conference, and I hope your time here will be memorable. And in the spirit of the coming holidays, I would like to wish you the most traditional and most valuable things, health and happiness. Thank you for your invitation.
Thank you. For these nice words, and of course, we hope that we will continue our collaboration with you, especially as a scientific secretariat, also with the whole academy. So you see that, in fact, we put on the fundament two fundamental things, as you said, math from one side and women from the other side. So these are the most fundamental things. One is in the science, the other in the life, but also in the science. And one good idea probably is to share your experience with connections with Japan. And for the next conference, maybe you will suggest us to invite some Japanese colleagues, women, yeah, which will be very interesting and enlarging not only our conference, not only to Southeastern Europe, but also, let's say, all around the world. Okay, so thank you once more. And finally, I would like to present you Professor Lyudmila Katsarkov, who is the scientific director of the International Center for Mathematical Sciences, who will say a few words via Zoom. So please, Lyudmila.
Thank you very much. I hope you can hear me.
Yeah.
So the conference actually was initiated as an idea discussed between Verichka Milusheva and myself during the time of COVID, and it proved to be a very robust and full of energy initiative, which was carried through the years by the dynamo that we have in Sofia, Verichka Milusheva, who put a lot of effort, imagination, and vision for science for the creating of this initiative and carrying it through. And so I feel a little bit guilty in front of each and every one of you, because she was an important part of the Kitchens conference last week in Miami, and probably this is where she actually got sick, so I apologize for this. It's all my fault. But hopefully she will recover and be with you. I'm very glad to see you all in Sofia in person now. And as I said, it appears that this is a very robust initiative promoting excellence of science for women in Eastern Europe. And we intend to enlarge and keep this initiative going, opening up to other Eastern and Central European countries in the next year. So I'm very impressed by all the names that are going to be giving talks today, tomorrow, and the day after, and I'm sure this will be a very successful conference promoting excellence in mathematics among women. So I wish you all the best for a very nice conference, a very successful conference, and let's not forget happy holidays to all of you. Good luck. Thank you.
Thank you. Okay, maybe we have a dear guest here also, the full member of the Academy, Professor Drensky. So it's a tradition for him to say a few words.
This is tradition for them to ask me to give them to say something before asking me for this.
Yes.
So every time I have to think something in the moment. And there is a principle in chess. When you are excited, so you have a short time, you should say something which you should say play the move which is the most unpleasant for the other side. And in my case, I should do just the opposite, to say something which is the most pleasant for you. You see, my father, he was a Navy officer during the king time when Bulgaria was a kingdom. So I had to have a very big respect to ladies. For example, my father will turn in the grave if now I don't give a hand to the lady when she goes out from the bus. At the same time, I should tell you that I have many female authors. Okay, there is only one thing that before to start to work with some lady, I have to ask permission of my wife. But this is of course normal, and only once I got a rejection. Even now I work with the young lady in Colombia. But also you see, Oleg spoke that there are ladies and mathematics there from both sides. But you see, mathematics is in Bulgarian, in Russian, in German, in Portuguese. This is female. This is die Mathematik, etc., etc. Okay, in French and Spanish, this is was mathematics or les mathématiques, again female, but there are many mathematics. Also, you see, from this point of view, there are two kinds of mathematicians. Some of them, they claim that there is one mathematics, and they do this mathematics. Some claim that there are many mathematics, they do their own mathematics. Okay, there is a third kind of mathematicians who claim there is only one mathematics, this mathematics which I do. That is not mathematics. And also, you see about mathematics, you should be, with respect to her, as a lady, for example, you know this famous expression of Gauss, that mathematics is a queen of science, and number theory is a queen of mathematics. So this is not king, this is queen. And finally, okay, I think that in all the cases, I think that women in mathematics, this is not only the beauty part of the beautiful part of mathematics, but also the results of some beautiful things. So I wish you a very nice conference, and also that to remember that there is one mathematics, and you should do this mathematics.
Okay, thank you, Vasily. I see among us another special guest. This is Miss Dimitrina Polivirova, who is the director of the National Laboratory of Computer Virology at BAS. If you want, you can say something to greet our guest.
Thank you for your invitation. Practically, I'm not a mathematician woman. I'm more also in informatics, but I wish you a very successful conference these days, and appreciate your efforts in this really difficult for me science. So good luck to all.
Thank you. So I think enough greetings. And I suggest to start our scientific program. And the first chairman is Professor Kyriakova. So please, Virginia, just
yes, I have the pleasure to open and to share the first session of this women conference. You know the program. It's a start for the first lecture to open. Let me present our first invited lecturer, Professor Eva Kaslik from West University of Timișoara, Romania. Well, her research interests in contributions in dynamical systems, stability, control, bifurcation, chaos, qualitative theory of impulsive and fractional of the differential system, dynamic of recurrent neural networks, mathematical models in aerospace, sciences, and so on. As 10 or dozen years ago, she was awarded as best young researcher in her country, her university. Now is established professor, and let me say also that she is a member of the editorial board of our specialized journal Fractional Calculus and Applied Analysis. So the topic of the talk, you see, is fractional differential equations and applications in neuroscience. So, please.
Thank you very much, Professor Kyriakova, and I would like to thank the organizers for inviting me. It is my first time here at this conference, and it's an honor to be here. It's my first talk, so probably, I mean, it's the first talk of the conference, so probably I'm a bit nervous. Can I just move a little bit just to be able to see also? All right, so I'm an applied mathematician. I work primarily in the field of fractional differential equations and delay differential equations and in mathematical modeling. And today I will talk about some applications of fractional differential equations in neuroscience. So actually I will start with a little bit of introduction and some of our results on the qualitative analysis of fractional order systems. And then I will show in which way fractional differential equations can be used in formulating mathematical models of biological neurons. I will focus mostly on Fitzhugh-Nagumo and Maurice-Leclerc type of models, and I will also show some recent results that we have obtained together with some of my collaborators. So, equations with derivatives and integrals of fractional orders are mainly used to describe systems which are characterized by non-locality, by power law, long-term memory, and possibly also by fractal properties. Fractional calculus dates back to the 17th century. Actually, there was this famous letter of Leibniz to L'Hopital, which mentions the derivatives of order 1/2. And since then, of course, there are very many big mathematicians who have dealt with the subject, and I would like to mention just a few, like Leibniz, Liouville, Riemann, Abel, Ries, or Wien, but of course this list is far from being exhaustive. Professor Kyriakova here is a specialist and most maybe the biggest expert in the field, so I will not go in the part of the historical background. So, all right. So in our work, basically we are concerned with the Caputo derivative, which is defined right here. Why we are considering the Caputo derivative? There are other fractional derivatives as well as the Riemann-Liouville derivative or the Grunwald-Letnikov derivative. We are considering particularly the Caputo derivative because it has some nice pleasant properties that makes it more suitable for mathematical modeling, in the sense that, for instance, when we are considering a fractional order system with a Caputo derivative, we can associate to it initial conditions of the usual form that we also encounter for integer ordered dynamical systems. I also put here the formula for the Laplace transform of the Caputo derivative of order Q. I will use this formula a little bit later for some of the qualitative results that I will be presenting. All right, so when I actually first started working with fractional order systems, our main focus was on stability concepts and stability properties of fractional order systems. So we'll just consider for the very beginning a general system of this form 1, okay, where Q can be actually a vector of fractional orders, Q1, Q2, Qn, all of them between 0 and 1, so we are considering only the case of subunitary fractional orders in our studies. The right-hand side function satisfies nice properties so that the existence and uniqueness of the solution of the initial value problem associated to system 1 will be satisfied. And basically, this is, for instance, the work of Witten, Zygmunt, and Tuan, who deal with some asymptotic behavior properties of solutions of linear, multi-ordered fractional dynamical systems. We have defined, I mean, in this slide I present some definitions for the main stability concepts related to fractional order systems. Of course, stability, asymptotic stability in the usual sense, but also it has to be kept in mind that in fractional order systems we will not have the exponential decay of solutions. So this is why we introduce a new type of stability concept, which is called the order of t to the power minus alpha asymptotic stability. This is also closely related to Mittag-Leffler stability. Of course, when we are studying nonlinear fractional order systems, a very important step in the qualitative analysis is the linearization process. And there have been several works concerning linearization of fractional order systems. Possibly one of the most cited ones is the work of Li and Ma, but this has been refined in the later years. Okay, so now when we look at linear systems with fractional order derivatives, in the simplest case, all the fractional orders in the system are equal. So we will end up with a system of form 2, and the characteristic equation which is associated to this type of system is simply given by 3. Okay, and it can be shown that the linear system 2 is asymptotically stable if and only if the spectrum of the matrix A is included in this set Q, meaning that actually we won't have roots for equation 3 with positive real part. Okay, now this is a complicated condition to satisfy given the complex power function which appears in the characteristic equation. So one result that deals with this problem is the so-called Martignon's theorem. I will explain just shortly what this is about, and also maybe just give an idea how this can be proved. So if we consider the matrix A in its Jordan normal decomposition, we are considering the Jordan normal form J with the corresponding Jordan blocks and eigenvalues. We have the index of the eigenvalue lambda k, which is obviously the size of the largest Jordan block associated to the eigenvalue. The geometric multiplicity, which is the total number of Jordan blocks associated to the eigenvalue, and the algebraic multiplicity, which is the sum of the sizes of all Jordan blocks associated to our eigenvalue. And then in Martignon's theorem, actually, it is stated that our linear system with equal fractional orders is going to be asymptotically stable of order t to the power minus alpha if the spectrum of the matrix A is included in this set SQ, meaning that the absolute value of the arguments of all the eigenvalues of the matrix will be larger than q pi over 2. There is also a limiting case. What happens when we have certain eigenvalues which have exactly the argument equal in absolute value to q pi over 2? Well, in this case, these eigenvalues have to satisfy that they are of index 1. So their algebraic and geometric multiplicities are equal to 1. Okay, we made a little correction to the initial theorem, particularly for this second special case, together with Roberto Garapa and my former PhD student, Juana Jantibur. Also, the correct version of the theorem appears in the previous book of Guy Dieter. Okay, so this is possibly the most important theorem which is used in the stability analysis of equal order fractional order systems. However, when we would like to extend to multi-order systems, so when the fractional orders are not equal in our system, things become much more complicated. Because obviously when we deal with a system of the type 4, where not all fractional orders are equal anymore, we cannot state that this will be equivalent to the associated system in the Jordan normal form, because simply we have different fractional orders. What I should say also, that I forgot to say on one of my first slides, is that when we deal with fractional order systems, actually these are equivalent to systems of Volterra integral equations with weakly singular kernels of convolution type. Okay. So, the extension to multi-order systems is quite complicated. Of course, we can prove a theorem which at least gives the theoretical characterizations for the asymptotic stability of such a system with respect to the distribution of the roots of the characteristic equation 5. However, since we have many different fractional orders in that equation, that becomes increasingly complicated when the dimension of the system increases. So what we managed to do actually was just to deal with two-dimensional systems, and I will actually present some of the results which are not at all easy to obtain. So let's just consider that we have two differential equations, linear differential equations in our system with two different fractional orders, Q1 and Q2, which are subunitary. The characteristic equation in this case is given by equation 7, so Q1 and Q2 are subunitary fractional orders. And so we can actually show that our two-dimensional linear system is asymptotically stable if and only if all the roots of the characteristic equation have negative real part. And if the determinant of the matrix A is non-zero, then and our characteristic equation has a root with positive real part, then the system is going to be unstable. So this is in line with what we know from the theory of integer order dynamical systems, linear systems of differential equations. However, explaining the distribution of the roots of this characteristic equation is not simple at all, because we have the two parameters A11, A22, which are basically the elements from the main diagonal of our two-dimensional matrix. We have the determinant, and we also have the two fractional orders, Q1 and Q2. Okay, so what we managed to do, actually, for the very beginning, we have explored fractional order independent stability and instability results. And we have obtained that if the determinant is negative, then our system is going to be unstable regardless of the fractional orders that we are considering. On the other hand, if the determinant is positive, then our system is going to be unstable if and only if these sets of inequalities from the first theorem hold. On the other hand, we have also obtained fractional order independent stability properties, saying that our two-dimensional system is going to be asymptotically stable regardless of the fractional orders, even only if these inequalities are satisfied. Now, the first set of inequalities here just tell us that the trace of the matrix is negative and the determinant is positive. And this actually corresponds to the classical Raud-Hurwitz stability conditions for two-dimensional systems. However, in order to guarantee that we will have asymptotic stability for no matter what kind of fractional orders we are considering in that system, we also have to impose this inequality. Okay. So these are our fractional order independent stability and instability results. For the fractional order dependent results, we have to introduce a smooth parametric curve in the A11, A22 plane for some fixed value, arbitrarily fixed value of the determinant, which is considered to be positive in this case, because when it is negative, we already know that we have instability. we have this smooth parametric curve defined by gamma, by the gamma curve. We list some properties of this curve, but I will show you just from a graphical point of view. So you will notice that in each of these graphics we have the determinant of the matrix is chosen to be equal to 4, so it's a positive value. And then we have Q1, the first fractional order, fixed to the value 0.6, and then we have different values considered for the other fractional order, Q2. So what we have over here, if you see this darker shaded, I don't know, pink region, this is the fractional order independent stability region. So if we pick A11, A22 in this region, for sure our system is going to be asymptotically stable for no matter what kind of fractional order. In the dark blue region, we have the fractional order independent instability region. And in the lighter pink and respectively lighter blue regions, we have the fractional order dependent asymptotic stability and instability region. They are separated by that black curve, actually the black curves in each of the graphs, which are basically the gamma curves that I have introduced on the previous slides, and which are basically obtained using the root locus method. Okay, so these represent the boundary of the stability region for the particular fractional orders that we are considering in each graph. Okay. Actually, you can notice that when the two fractional orders are equal, then our curve just becomes a straight line. All right, then in this other graph, we have actually represented all possible curves that we have obtained for different values of Q1 and Q2, so both fractional orders between 0 and 1. I don't remember exactly how many we have plotted there, but the nice thing that we have observed and that we also, of course, expected based on the theoretical results is that all these curves will fill in the region between the fractional order independent stability region and the fractional order independent instability region, respectively. Okay. So this is actually based on our work from fractional calculus and applied analysis from a couple of years ago, and it is also part of my PhD student's thesis, which was presented in 2020. So this is the main theorem which summarizes our results about fractional order dependent results based on what I have explained previously. Okay, so actually these are, they look, I mean, the two-dimensional system is not extremely complicated, but still, obtaining all these results is not a very easy task. And also, generalizing to higher dimensional systems becomes almost impossible due to the high number of parameters that is being involved. Already for three-dimensional systems, we will have plenty of parameters to take into account. However, we can use these results for more complicated systems as well, in case the characteristic equation that we are studying will decompose into several factors of this type. And this is what I will show a bit later in my talk. Now I will go to the different, to the next section, which deals with the neuroscience applications. For the beginning, I have just inserted this nice graphical representation of a biological neuronal cell. So the biological neurons are obviously the building blocks of our nervous systems. We have around 85 billion or more neurons in our brain. So the neural cell is made up of the cell body, which is the soma. There is also a dendritic tree formed by dendrites, which actually capture the signals from other neurons and transmit them through the cell body, through the axon, towards other neurons. Okay, so the main function of neuronal cells is to receive signals from other neurons or for external sensory cells, and just process that information, process that signal, and then transmit it along the neural axon towards the other neurons. Of course, so here when the connection is also for the synapse. All right. How is this information, how do neurons communicate with each other? Actually, there's the neuronal membranes are charged, meaning that we will have a difference of potential between the inner part of the neuron and the external part of the neuron. And we also have in the neuronal membrane some voltage-gated ion channels which open in response to changes in the membrane voltage. So when the membrane voltage actually reaches a certain threshold level, these gates will open and ions will enter the cell or they will leave the cell. This is actually information transmission or signal transmission by the neuron to another neuron is made using these action potentials, and here we have a short description of what the action potential is made of. So when a certain stimulus excites our neuronal cell, depolarize towards a certain threshold potential, which is reached over here, and if this is reached, then the sodium channels, the sodium ion channels will open and our membrane is going to depolarize. Okay, until it reaches a certain peak action potential, which is at point 3. And when this peak action potential is reached, the potassium channels will open and potassium ions will start leaving the neuronal cell. At the same time, the sodium channels will close, and then the membrane will become hyperpolarized. So then it will enter a certain refractory period, and it won't be able to fire. And then, of course, all this is repeated. So actually, how the neuronal signal is transmitted is through a train of action potentials. Okay, and now what why are fractional derivatives used in neuroscience? Actually, there are certain explanations, and there have been a lot of works on this topic, particularly in the last 20 years or so. I am not a biologist or a neuroscientist. I'm just trying to understand also these concepts. So, but the first papers probably which have considered an experimental foundation to why fractional derivatives should be applied or used in neurosciences were the papers of Anastasio and Lundström. Okay, so in the paper of Anastasio, actually, they showed that the frequency response of the firing rate relative to eye position of premotor neurons in the ocular system exhibit fractional order dynamics, and they drew this conclusion based on experimental results. On the other hand, the paper of Lundström in 2008, which was published in Nature Neuroscience, showed that when sinusoidal stimulus is applied to the neuron, the firing rate of neocortical pyramidal neurons can be well approximated by a fractional derivative of the input. Okay, so these are some of the papers for the experimental foundation of using fractional derivatives in neuroscience. But actually, from what I have researched, there are like 3 main directions which are being considered. And the first and most important one possibly is anomalous diffusion. So it has been proved experimentally that the movements of ions and neurotransmitters within and between the neurons can exhibit anomalous diffusion, which is not the same as simple Brownian motion. And actually the team which was involved in this experimental research was the team of Fidel Santamaria from the University of Texas, who published a series of papers regarding this subject, and possibly the first one was the one discussing anomalous diffusions in Purkinje cell dendrites caused by spines. So the dendrites that I have also talked about a bit earlier, this dendritic tree actually is responsible for receiving signal from other neurons, okay? And the dendrites are often in classical mathematical models, they have been just modeled using a simple cylinder like this, considering normal diffusion. However, in many cases, and of course there are many different types of neurons, but particularly in Purkinje cells and also other types of neurons, the dendrites are covered by some small protrusions which are called spines. And they are very rich in neurotransmitter receptors. So what happens is that the molecules are not, do not exhibit a normal diffusion, but an anomalous diffusion, a subdiffusion, due to the presence of these protrusions, which are the dendritic spines. So this was possibly the first research result which has considered anomalous diffusion in neuronal cells and showed this experimentally as well. So starting from this, there was a series of papers by Henry Langlands and Weir which constructed fractional cable models for neuronal dendrites, and they started from a modified Nernst-Blanck equation to generate a fractional Brownian motion, or on the other hand, a continuous time random walk. So in the two cases, we have different considerations for the diffusion coefficient, and these modifications of the Nernst-Blanck equation actually led to the formulation of fractional cable equations, which are presented over here. These have also been investigated in later years, and there's a very good paper of Mainardi and colleagues in 2018, which also summarized some very important results on the topic. Okay, so the first reason for incorporating fractional order systems or fractional derivatives in neuronal models was anomalous diffusion. However, what we have been concerned with in our research investigations was the incorporation of temporal derivatives. And this can be explained by complex temporal dynamics, which are often exhibited by neurons. It is known actually that neurons operate over multiple time scales. At the millisecond scale, we have action potentials and synaptic transmission. We have a second scale between seconds and minutes, which is responsible for short-term plasticity and neuronal adaptation. But also we have an even slower scale of hours to days, which is associated with long-term plasticity and memory formation. Fractional derivatives have often been used in modeling processes that operate over multiple scales of times simultaneously. And again, it was the team of Fidel Santamaria who discussed these considerations in their paper on neuronal spike timing adaptations for fractional leaky integrate and fire model. Also in this picture, actually, we have a short representation of multiple scale dynamics for neurobiological read-write memory. So, which is composed of the spiking activity, which corresponds to computation, and silent process, which corresponds to storage. So it can be seen actually that spiking activity corresponds to faster timescales, while silent processes, the storage, corresponds to slower timescales. Okay, and finally, a third reason for considering has been conjectured that the physical meaning of the fractional order in fractional derivatives is the index of memory. Fractional derivatives have an inherent memory property which actually makes them useful for modeling biological neurons. And based on this explanation, actually Wienberg in 2015 has introduced a fractional order model of the Hodgkin-Huxley type. I will present it straight away. So the main idea is that we are modeling the passive cell membrane as a parallel resistor-capacitor circuit with ideal capacitive behavior. This is at the foundation of very many conductance-based neuronal model like the Hodgkin-Huxley model or the simpler Fitzhugh-Nagumo-Maurice-Leclerc mathematical models. However, it has been hypothesized by Westerlund and Ekstrom in 1994 that if we consider Jacques Rie's empirical law for current through capacitors and dielectrics, actually we can model the capacitive current voltage relationship for a non-ideal capacitor. Now, this is still a problem that is being investigated. It is not very clear what the physiological source of such a non-ideal capacitive behavior would be in the case of neuronal cells. However, it may arise due to the fact that the electric properties of the membrane are not homogeneous. Okay, so Wienberg analyzed the fractional order Hodgkin-Huxley model by considering a fractional order temporal derivative to describe the membrane voltage V. And here we have N and P, which are gating variables, which correspond to the sodium, potassium, and other type of ion channels. Okay, so I will present some of our results in the field, and I will start with a simple conductance-based model, which is the fractional order Fitzhugh-Nagumo neuronal model. It is a simplified version. Here we just have two fractional order differential equations. We have considered two different fractional orders, Q1 and Q2. V is the membrane potential, W is a recovery variable, I is an external excitation current, and we consider the fractional orders to be between 0 and 1. Actually, in the most common case, we can consider the second fractional order, the one which corresponds to the gating variable W as being equal to 1. Okay, we can rewrite our Fitzhugh-Nagumo model as a conductance-based model presented in system 9, where this function I depending on V and W is simply a third order polynomial, and W infinity is just a linear function. So in the case when alpha is smaller than 1, alpha being just 1 over this parameter B over here. Actually, we analyzed both cases, but today I will present just the case when alpha is larger than 1. Based on our qualitative results that I have presented at the beginning of the talk, we can actually fully analyze the qualitative behavior of the system in a neighborhood of the equilibrium. If we plot the path of equilibrium with respect to the external input I for those values of the parameters from the system, I don't know if you can see that there are two colors, a red and the green color. No, actually it's red up until here and then it's green. Okay, so what do the colors mean? Actually, the red color means that the corresponding equilibrium will be asymptotically stable for any kind of fractional order that we would consider in the system. And for the green part, the fractional order, actually the asymptotic stability will depend on the fractional order that we choose. We can plot the so-called stability regions in the Q1, Q2 plane for the corresponding equilibrium point. So here we have selected several values for the equilibrium potential, V0, 0.2, and so on. And based on our qualitative results, we were able to obtain exactly what is the set of fractional orders that correspond to the asymptotic stability of the equilibrium. Since we are considering Q2 to be larger than Q1, we are only interested in the region above the first bisector. Okay. Of course, if we would like to use our qualitative results in order to see the behavior of our neuronal cell, we are not interested in asymptotic stability. We are interested in instability. So we have to, actually we can obtain, based on, again, our qualitative result, what is the region of fractional orders and parameters that have to be considered, which will guarantee that the equilibrium is not going to be asymptotically stable, and so it will exhibit, so our system will exhibit more interesting behavior from a mathematical point of view. And what we can notice over here is that for these values of the parameters, we have the equilibrium point over here, and the critical value Q1 star of 0.599 can be computed for a fixed value of the second fractional order Q2 to be equal to 0.8. And we can see in the numerical simulations that in the integer order case, our behavior would be like this. In fractional order cases, we get more complicated behavior, smaller oscillations followed by larger oscillations, and these correspond in a better way to the experimental behavior of biological neurons. So what we observe here are some mixed modes of oscillations, small oscillations followed by the spikes, and then again small oscillations. Okay. Of course, we also wondered what happens when we couple two such models, and a little later we will also deal with networks of such neuronal systems. So if we take a coupled system of Fitzhugh-Nagumo equations, such as in 10, here G is the coupling parameter. Then in this system already things are much more complicated than previously, because we might have a lot of equilibrium states, not only one. So in these pictures actually we have the different number of equilibria that we obtain in the system depending on the coupling parameter G. We can analyze the stability of the equilibrium states based on our qualitative results that I have presented at the very beginning. And this is due to the fact that at an equilibrium point, actually we can notice that the characteristic equation decomposes as a product of two such terms that we have already investigated. So this is a special type of system which, even though it is like four-dimensional, the qualitative analysis can be reduced to what we have obtained for two-dimensional systems. Okay. So then we can obtain fractional order independent and dependent results based on our qualitative analysis. Actually, we can fully characterize the stability properties of such a coupled system of Fitzhugh-Nagumo neurons, but I will move a little bit quicker along these slides. This is the special type for the trivial equilibrium, and here we have some numerical simulations, again, for the case when we only have the unique equilibrium in the system. Again, we can notice that compared to the integer order case, which is presented in this last graph, the fractional order dynamics is a bit more complicated, and again, we observed these mixed mode oscillations, which are not present in the integer order system. On the other hand, we might also have the case when we have many equilibria in the system, For instance, here for these values of the parameters, we obtain 5 equilibrium states. 2 of them are always asymptotically stable for any type of fractional order. 2 of them, the next 2, are unstable for any choice of the fractional order, while the trivial equilibrium is actually asymptotically stable only for a certain region of fractional order, of fractional orders. And for instance, this can be seen in these 2 graphs. For the second fractional order is actually considered to be equal to 1, so it's integer. And for Q1 0.8 we have convergence towards the 0 equilibrium, while for Q1 0.95 then the convergence will be towards one of the first 2 asymptotically stable equilibrium points. So it is quite difficult to predict what will happen in larger systems of Fitzhugh-Nagumo models. I would also like to present in this last few minutes some results about the fractional order Maurice-Lacquard neuronal model. This is also a conductance-based model. In this case, we have considered same fractional order for both of the variables, the voltage and the beating variable. The reason for this was that we have also studied a large network of such Maurice-Lacquard models, and we wanted to keep things a bit simpler. What we have noticed in this particular single neuron model was that actually, again, we can observe more complicated behavior in the fractional order case than in the integer order case. And in these graphs, actually, for the values of the parameters which are mentioned above, we find the critical value of the fractional order Q star, which is given over there, again, based on the qualitative analysis. And the numerical simulations actually show, maybe we have to read them from the right to the left. So for the integer order case, we just have oscillations, simple, they are called sub-threshold oscillations. But as we decrease the fractional order Q to 0.85 and then to 0.83, what happens is that the living cycle approaches the equilibrium point, which is over here at the intersection of the two null lines. And this interaction between the limit cycle and the equilibrium point actually generates some smaller oscillations also around the equilibrium point. And then for 0.8 we can see these oscillations a little bit more clearly. So again, this behavior is called mixed mode oscillation, and this in integer order systems, neuronal models can only be observed for 3-dimensional systems, not for 2-dimensional systems. So in the case of fractional order neuronal models, we can get more complicated behavior that is observed in biological neurons, and actually the subthreshold oscillations, small ones, which are interspread in the mixed mode oscillations, they create a time scale at which information is communicated among neurons. And now we have considered a network of 2 subpopulations of Maurice-Lacquard neurons. The network is described by this system of 2n fractional order differential equations. We have considered an Erdős-Rényi random graph for this network, and we have considered 2 subpopulations. One of them with 1 fractional order alpha, and the other subpopulation with a fractional order beta. Actually, in the numerical simulations that I'm showing on this last slide, we have alpha equals to 1, so the first subpopulation is considered to have integer order alpha, and it is made up of 60 neurons, while the other subpopulation corresponds to a fractional order of 0.75, and it is made up of 40 neurons. So the integer order subpopulation is an oscillatory subpopulation, because if the two parts are not connected, or we just take a neuron from that subpopulation, we will just have the oscillations. On the other hand, for the other subpopulation corresponding to 0.75, each individual neuron, if it is disconnected from the network, is going to be in a quiescent state, so it will not present oscillations. What we notice is that when we couple our network using this random graph, so first, in the first graph here, we can see that for a small value of the connection coefficient, we have just plotted in this graph one randomly picked neuron from the first subpopulation, the oscillatory one, and another one from the other subpopulation. So basically, we can see that one of them is oscillating, the other one is in a quiescent state. As we increase the connection coefficient, so for 0.05, we can also notice that the excitable population, which in disconnected case was in a quiescent state, it starts presenting irregular firing and bursting. As we further increase the connection coefficient, then we will also see regular bursting, and when the connection coefficient is 1, we will have synchronized periodic spiking. Okay, so this is what we actually one of our last results on networks with two subpopulations. And there are a lot of open questions in this domain. I tried to present an explanation on why fractional derivatives are considered in neuroscience models. We can see that fractional single neurons, single neuron models exhibit more complex dynamics than their integer order counterparts, as I showed in the graphs. It is possible to do an analytical analysis of larger neurons of such of larger networks of such models, but it is complicated. However, of course, we can rely on numerical computation. And of course, there are a lot of open questions here. One of them is what would be the thorough biophysical interpretation of fractional derivatives? What would be the role of fractional order neuronal models in disease modeling? What type of fractional order derivatives should be considered? In general, Caputo derivatives are used for their simplicity, probably. Also, if it is worth considering spatio-temporal dynamics, so models which incorporate temporal fractional derivatives, but also anomalous diffusion term. And there has been a discussion just 2 weeks ago at a workshop in the Netherlands regarding the fact that neuronal structures present fractal, let's say, fractal not behavior. Yeah, so neuronal structures actually
Fractal structures.
So neuronal networks present a fractal structure, and that this could be a further explanation on why fractional order derivatives could be incorporated in such models, in network models. But again, this is an open question to investigate. So thank you very much for your attention. These were a few of the results that we have been working on with some of my colleagues, and I'm again very grateful to be here. So thank you.
Do you have questions, comments?
Thank you very much for very interesting, incredible presentation. I have a question, remark about the first part.
First part.
Well, you don't need to show.
Yeah, sure.
For the case when all the orders are equal,
yes,
you need this argument of eigenvalues sitting in some sectors. Have you heard of something called the matrix sector function? Well, it's basically you take a matrix and you put in corresponding a different matrix where you take in every sector, you divide all the employment sectors, and you put all eigenvalues sitting in that sector into the corresponding root of units on the unit.
Okay.
And so basically, if you don't want them to be in a sector, and there are some good algorithms for approximating this. So if in a certain step of algorithms your null eigenvalue is being attracted to this unit root which you don't want, then you're done. Then you don't have eigenvalues in the sector. So maybe.
Thank you very much for the suggestion. Actually, I will look into
something called matrix sector function. We had a paper, but there are more. I was co-author of one 10 years ago. And about the case when different orders, it's kind of obvious question when you study this whole stability problems. Doesn't it help to assume the orders are rational?
Yes, of course. If the orders are rational, then we have a commensurate system. We can transform it into a system with with equal fractional orders, obviously. But if they are not rational or not, if their ratio is not equal to rational.
Does it have any really effect on the model? I mean, because in your numerics they are always rational anyway.
Yes, in the numerics it's rational anyway.
Well, then it reduces on the problem kind of reduces to some geometry equation.
Yes, but then the dimension also increases very
much. The dimension increases
so
that
can be,
This
can be so that might be a bit more complicated. Okay. I think there's also one question, but I cannot.
Yes, I have a question if possible.
Yes, sure.
In your last slide, you meant just a moment, maybe I have to double. In your last slide, you mentioned spatial temporal dynamics.
Yes.
With a question mark.
Yes, with a question mark. Yes.
So my question, whether the question mark is because you also support from your them to the spatial temporal, or you don't see any connection?
No, of course I see connection. There's an echo, but of course there is a connection. And actually, at the beginning, when I talked about anomalous diffusion, I presented a fractional cable model which had a spatial fractional derivative. On the other hand, the other models incorporated temporal fractional derivatives. So my opinion is that possibly it can be really useful to incorporate both types of fractional derivatives, the temporal one and the spatial Laplacian into such a model.
So it doesn't contradict synchronization?
No. Thank you very much.
Yes, madam. I have a question from the statement. In the middle of your talk, and I will be happy if you return back to it, where you explain the correspondence between these neural processes and the application of your model. In this point, I would like to look more slowly at this. Yes.
This part?
This part, yes. Can you just repeat it for me more slowly to understand how they fit?
For the anomalous diffusion part, so in the anomalous diffusion part, actually it was shown experimentally that the dendritic spines cause anomalous diffusions through the spines. Initially, in the cable model, it was considered that the spines are just modeled as a cylinder. However, they have these small protrusions, which are the spines, and due to their presence, actually the molecules cannot diffuse like in a very simple way. And this is what causes anomalous diffusion in this.
And how it fits to the model, exact model which you present? Yes.
This one, actually, this is the way the fractional cable actuations have been obtained. That they started from modified Nernst-Planck actuation, and they generated the fractional Brownian motion and continuous time random walk in considering different diffusion coefficients. And starting from that, they consider the fractional table of actuations where you can notice the diffusion coefficients over there. But this is, again, something that I have not covered. I am interested in working in this direction as well, but I think that the main results have been probably the best summarized in the paper by Mainardi.
Okay, thank you very much.
Some other questions or comments? Then,
thank you.
Thank you. We're exactly on time with our program, and we will proceed with the next talk. I will present
Talk after the one we just heard, it was absolutely excellent. And especially difficult that I also will tell you about applications of mathematics in biology. In my talk it will be more biology, less mathematics. Actually, this talk is devoted to cancer stem cells population behavior, and the most important issue here is to show how to find appropriate mathematical model, appropriate mathematical structure to answer concrete, important biological question in hands. So, initially, cancer stem cells was not named cancer stem cells. They were named, when they were discovered, tumor-initiated cells. And they were found as a population, inside big cancer population, which exactly responsible for initiating tumor growth in new places, and also resistance to chemotherapy and radiotherapy treatment, which is very important because exactly the presence of these tumor-initiating cells is responsible for relapsing of cancer after treatment. So later it was found that some other characteristics of cancer stem cells, of tumor-initiating cells, are similar to normal stem cells of adult tissues. It is not stem cells which are embryonic stem cells, that is a special story. But in our tissue, in all our tissues, there is some small fraction of stem cells which are responsible for replacing damaged or died cells in our tissues. So the similarity of this tumor initiation fraction with normal stem cells of adult tissues rose the question, cancer stem cells and normal stem cells, more similarity or more differences? Meanwhile, this question was asked and worked out. Tumor-initiated cells start to be named cancer stem cells. So this is a fraction somehow responsible for tumor growth. But the behavior of this population, and the main features of it were very interesting for biologists because, as I said, it was very important to cancel this population to avoid the relapsing of cancers. So, main characteristics of normal adult stem cells: ability to regenerate a tissue, like in cancer stem cells, small percentage in total population, of course, and slow rate of cell division. And the most important feature of normal stem cells is asymmetric, so-called asymmetric cell division. It is very strange for mathematicians because this asymmetric in biological field means just stem cell, when it divides, produce two cells, differentiated daughter cell and stem cell. So this asymmetric means unlike two identical cells here, it is two different cells. So this is asymmetric division in stem cells and symmetric division in non-stem cells. So the main question was, for example, if cancer stem cells has this behavior. So asymmetric cell division was the most important question to compare between cancer stem cells and normal stem cells, also slow rates of cell division. The interesting thing here is that a lot of things in biology still can't be seen by biological methods only. We need mathematics like an analytical microscope, which can, by metallization, find the questions which are not clear and can't be detected just by biological means. So these questions and some others were the point of the modeling, but not only them. So, cancer cell culture in which we can have this specific population, cancer stem cell population, can be identified in the culture due to specific cell markers, then it could be purified from the culture, and then this pure only stem cells population can be again put in culture, and its behavior can be detected. And it is very interesting first phenomenon, very, very special, very, very surprising, that if we have 100 stem cell population, 100, and put it in the culture, very quickly, these cancer cells, and if you measure the percentage of cancer stem cells every day, this is days, yes, we can see that cancer stem cell population decreased from 100 to 1 or 2 or 3%, and then stabilized in the characteristic percentage level, characteristic for this cell culture. This cancer cell culture, if you take one cancer, it will stabilize 1.5%, which is characteristic for this lung cell culture. If you take ovarian or breast where 3%, it will be 3%. So somehow cancer population knows its structure, at least one-dimensional structure, percentage of cancer versus cancer stem versus non-stem cells, and has some intrinsic ways to support this population after any perturbation. So it is very important to understand what mechanisms underlie this interesting phenomenon. And exactly this was one of the parts of our model. It is, of course, was shown with mathematical equations, but they are so simple that I will not give it to you. Even without mathematics, it is clear that having these two types of behavior, stem cells only asymmetric, so replacing itself, and 1D, and D then symmetric, it is absolutely impossible to have the stabilization. It will not possible. If we have 100 of stem cells initially, and then we have this situation, we will never have stabilization. It will go up to almost 0. But we have this phenomenon. So one question is what underlies the stabilization of cancer stem cell population? Second question, in reality, what scenarios of cell behavior exist in a given type of cancer? If we have this curve, stabilization at this place, what exactly scenarios of behavior, like asymmetric or symmetric or something else, exist in a given type of cancer? And the most interesting for medical story, what does the non-stem to stem transition exist? So one of the possible scenarios in behavior is that non-stems start to be stem, and when this transition exists.
Sorry, but what the stabilization level, it depends on what? On a type of cancer, on a specific...
Only on specific, even not a type, and specific cell line. For example,
specific
cell line. It could be, for example, in ovarian cancer, it could be line 600 for 8 and line 600 for 5. And they will have different levels, but absolutely the same. If you need to support cancer population for years, and for years it will be the same.
And what it depends on, if you take...
It was exactly, depends on some intrinsic properties, which mechanisms for which we try to discover, and maybe discover a little bit, but what is governing it, we don't know. But some mechanisms we were able to discover. It is really very good mystery, yes. So each each population knows its structure and supported after any perturbation. It is absolutely amazing. So we are trying to answer all these questions. And non-stem to stem transition, as I said, very important, again, to prevent relapsing of cancer, which depends on stem cells. If we cancel stem cells, but not cancel this transition, we have stem cells again.
It is through this Yamanaka factor, so how does it happen?
This is already, I appreciate questions on the way for understanding, but questions for discussion, let's leave on the end. Okay. Otherwise, you will never come to this end. So, our goal of mathematical modeling, that precise goal, giving an experimentally measured curve. This is what I showed, perturbation from the normals, usual cancer culture, perturbation, pure cancer stem cells, and then stabilization curve. So given an experimentally measured cancer population dynamics, to find what scenarios of cell behavior exist in these cancer cells. In our population, we have only two populations, stem and non-stem, which we named D daughter population. Okay, so, and our mathematical modeling is very simple, as I already said. On what depends this simple population? Patterns of cell division, symmetrical, asymmetrical transition, rates of cell division, and rates of cell death. Only these three factors influence the population structure. And what we assume? Theoretically, we assume that stem cells can have asymmetrical division, as it was reported initially for cancer stem cells, but also, and it was reported later, it is symmetrical to D, symmetrical to S, and direct transition from S to D. These all types of behavior were appeared in different papers and in different groups of researchers. For D cells, usually suggested only one behavior, but we deal with cancer. So in cancer, we assume the same four possible scenarios, actually theoretically, but then we assume that exist only two scenarios. This one, normally well known and usually suggested, and D to S transition. This is what I explained. Non-stem to stem transition. Because all others can't be happen in D cells and they're prerogative of S cells. So here we will take only two scenarios for our consideration. And for each type of scenarios, we put the probability of its occurring in the stem cells after perturbation. We have six probabilities, 4 for stem cells, which are P the probability for stem cells, and 2, as I explained, scenarios for D cells with probability Q1 and Q2. And we have, this was somehow measured, the constant division and death rates, but different for stem and non-stem. All these considerations give us very simple system of equations. It's just ds over dt, s, big S, it is stem cells, which the amount of which changing in cell culture after perturbation, depending on gamma, it is cell death, coefficients of probabilities of different scenarios with corresponding coefficients multiplied by lambda cell speed of cell division, and the same for D. The changing of amount of D cells in the culture depends on this rate of division and different scenarios, P and Q correspondingly. So, by this is like a very simple story for first grade students. We can find the d small s over dt. D small s is percentage of stem cells in the total population. And now we're trying to find what P and Q, what probability of scenarios of cell divisions should be in our equation in order to best fit the experimental curve and our C small over T, our curve which we found in, as a solution of this equation. So, maybe I will skip this also very simple part. This is just to say that in order to have more equations for better solution of our system, we need to initialize some additional step. So we came under the problem that we need additional two equations, and we found the possibility by new hypothesis. This new hypothesis is just theoretical one, very helpful, but not proven yet. It is difficult to prove. The sum of all changes in cell behavior scenarios up to stabilization should be minimized at each step. At each step means at each time point. Because the logic for this hypothesis is that cells are very big mechanism. And to jump from one scenario to another, from asymmetric to symmetric, or from division to transition, it needs a lot of things to be prepared. So as minimal change should be done in all set of scenarios, as better the system can produce its behavior next step. So we have this hypothesis which gives us additional equations. You can see it. Okay, you can see it here. So we have the request to minimize all these three probabilities. The three probabilities gives us requested number of all equations to describe the system, and we have the result. This is our curve, this is our curve, and we have 6 corridors of probability. We have 6 corridors of probability corresponding to the families of solution for each probability. For example, P1 probability of asymmetrical division has the corridor from almost 0 to 75%, and some other has different corridors also. So this is very good initial result to show how scenarios should be in order to be able to fit to this curve. But the question is, so this is, we have these curves in different conditions of different set of rates of death and rates of death and rates of division in different cell cultures. So we can see that some of them are very close and some of them are very different, depending on speed of the divisions. This is experimental data. And very interesting to find unique solution for each corridor, which depends on initial conditions. Unfortunately, this is one of the things which biology for now can't give us. They can't measure the percentage of asymmetric or symmetric division in the culture because everything what considering stem cells is a very, very small population, 1%, and it is very difficult to find the possibility to detect it biologically. But we found very important thing. For example, mathematics again helps. For example, if we say we try to find through all these corridors of probabilities these conditions maximizing the probability of asymmetrical stem cell division scenario, so this very important question, asymmetric cell division in stem cells, yes or no, or how much, we maximize the request for this P1. And what we have, you can see this blue line in all different types of cell lines. And you see that it is not higher than 70%. Not sometimes even smaller. This means that in cancer stem cells, asymmetrical cell division, definitely not the unique one. There is definitely another scenario of stem cells. And this is the result important for several things, theoretical and medical at the same time. Another request, also very important. We say that we would like to minimize probability of non-stem to stem transition. This is what I also said. This is very important for preventing stem cells propagation. And we see what is going on if we have a request for minimizing this non-stem to stem transition. What we see in some, maybe it is too much light. This is a dark yellow curve, and in some cases it is really considerable. But in some cases you can hardly see it, but it exists. So this is never can be seen biologically, but we see that some percentage of non-stem to stem transition exists in all, at least these 6, all different cancer cell lines. So it is very important. Now, back to your question, and back to our question, and back to all questions. Okay, we found that scenarios of cell divisions changes with time. Okay, we found it. But what and how govern them to do so? So for the cells in the culture, we consider that probabilities of all scenarios of S and D cells are functions of a set of secreted factors in the cultural media. And it is very important because cells in the media secrete a lot of factors. We assume that these factors and the set and the amount of these factors are the mechanism which says to cells what to do, what scenario they're supposed to undergo. Okay. So our question now, given a set of unique functions of probabilities, P and Q, is it possible to find a set of factors, U, responsible for their dynamics? For example, we take this the set of these 6 curves, and we want to find the set of factors which will give exactly this dynamics of all 6 probabilities simultaneously. We decided that factor u of t in the media is supposed to have this shape, because corresponding to this formula on the top, okay, you will see. Because at some point this factor appears, then it grew, then it lives for some time, and then disappears. Or not, then it will be up to the end of the experiment. So, and we have A, B, C, and M 4 parameters of this curve. Actually, the parameter M we put as a stable from the very beginning, and we have only 3 parameters which we can play with. So then the dependence of factors P and Q on this factor U will be like this, as you see, where Y it is the variable for P and Q together, 6 for P to Q. And K is the number of factors which are supposed to be considered. This will go out of numerical simulation, which we will do next. And coefficients A and C reflect details of a particular factor K. So the width of this curve and the place where it is located on the curve. While the coefficient B, we set as a maximum from BIK, which means that it is a concentration of a biochemical compound in a medium. So, we will find coefficients B, A, and C, which provide this minimization of the difference between experimental curves. We have 6 experimental curves, as you remember, 6 experimental curves, and our computational numerical simulated curve. Then, for minimizing it, we need to ensure equality to 0 of this expression for coefficients A, B, and C. This is again big but simple mathematics. And in the end, we created a computational tool for prediction of a set of secreted factors involved in the controlling of cancer stem cells behavior. So the input for this computational tool is experimentally measured kinetics, initial kinetics, then experimentally measured rates of division and death, and determined set of probabilities, which we found in the first part of the talk. So we have 6 curves of probabilities. And the output of the curve is prediction of K functions. It is minimum functions which supposed to be present in the media with their specific patterns which can ensure these 6 curves to be implemented. And the additional experiment, of course, which should be done, which is still, this part is still under confirmation of our colleague experimentalists, together with this initial experimental curve, in each day point, they measure the so-called secretome, the set of secreted factors. And I show here 7 of them with absolutely different dynamics. Normally it's more than 100. And our tool predict the patterns of these secreted factors influencing our probabilities of scenario specifically in this way. So by comparison experiment and prediction, we can choose by the behavior the factor which is supposed to be involved in the story. Now our experimentalists try to add or exclude this factor from the secreted media and see how the behavior of cells change. Okay, I have enough time, but I think I will not concentrate on this part too much. This is actually ongoing work. It is already finished work, but not published paper. So this is again very interesting phenomena, second interesting phenomena, which is important to understand, and again mathematics can play a very important role here. It was shown in the lab of our colleagues that after radiation, which is supposed to kill cells and supposed to kill cells together with stem cells, or according to our knowledge, now it could be radiation plus some biochemical factor killing the secreted factor in the media responsible for stem cells, for non-stem to stem transition, or stem cells double division. So it is something which already used very widely to kill cancer cells. But it was shown that after radiation, there is phenomenon of post-irradiation induction of cancer stem cells. They were named induced cancer stem cells because after radiation, which is supposed to be killing of the cells, it produce the stem cells which are the most dangerous for relapsing a new cancer proliferation. And our colleagues made a very interesting experiment where they marked in the chromosome the markers of stem cells are on the cell surface. So this is how we can purify them and manage them. But they marked stem cells and non-stem cells in the chromosomes. So with the marker which is blue or red. So non-stem cells are always blue, as stem cells is always red. And then after radiation, they see blue cells with cancer surface. So this is induced cancer stem cells. So our task was using our already developed methods to find which scenarios lead to this very unpredicted and dangerous phenomenon. And let's just show the result. Okay, so it was our result showed that exactly, because it was not clear which mechanism, which scenario is responsible for this induced cancer stem cells. And our results showed that it is exactly non-stem to stem transition which responsible for this. This is this curve. This is numerical simulation for red cell population. So exactly non-stem to stem transition responsible for this unpredictable irradiation induced cancer stem cell results. So this how using the additional biochemical factors, it could be minimized and not being in the story of the cancer tree. That's all. Thank you very much.
Thank you.
You have question. You have question.
But I understood. Did I understand correctly that you do know the biochemical factors?
No, we don't know. We predict their behavior. Then biologists do additional, as every day they measure the percentage. Every day they measure so-called secretome. So it is a biochemical list of 100, 200 different peptides, sugars, glycocorticoids, many different guys. And we suggest that having the prediction of minimal, because everything in biology is supposed to be minimal, not too much, minimal factors which will ensure this thing. So by comparison, they can found we suggest the candidates, but then they should and now they are checking.
So the obvious candidates like this Yamanaka factors and whatever.
What factors?
Yamanaka, I think, the guy who got the Nobel Prize for discovering that this induced.
No. Okay, you mean this Chinese? Okay, I understand.
Japanese.
Japanese. Yes, no. The Japanese guy found completely different story. He found that the mutations in four genes can initiate not cancer stem cells, but just pluripotent stem cells.
Yes, going back somehow.
Yes. But it is first of all not about cancer. I always say that the name cancer stem cells are very tricky. They were tumor-initiated cells, and as you see, they don't have 100% asymmetric division. They have some other features.
So this must be different.
Yes, this is and this is not, and we don't work with genetic part. We don't. He found genetic genetic elements which activating, being mutation for permanent activation, mutated in cell can make it pluripotent cell, and this is genetic biology, and we more cell biology. We talk about cells, not about genes. So this is we just modelize what we see by results, not change cells.
Okay, but then another obvious probably has been done many times. But then you have this level of stabilization of you said of different cultures very different. What happens if you mix a little bit? You take some percentage of this culture, you mix with that. What happens?
We never did this experiment, we or our colleague. But what they did, they did interesting experiment. The two part of the flask. And one with 1%, and another with another percentage.
Yeah, that's what I mean.
Exactly. And finally, in both, it will be the same percentage. Finally, both come to the same percentage, like 1.5. And the membrane between
I mean, you mean they mixed?
No, they don't mix them. They didn't mix, but put the membrane.
Which separated them.
They separated cells,
yeah, this
but
is
the
more
membrane,
clear.
but the membrane can.
But it sounds like mixing will help you to understand the underlying math.
Yes, the mixing.
If you know what happens with mixing, then you kind of can feel what is the underlying.
Some experiments of mixing also was done. I mean, 5% of D.
Yeah.
it was done, but I don't remember that. I think they did not get any interesting results from it, yes. More interesting is that we don't mix cells, but mix the media, you see? The media, the secreted factors cannot move, and we can expect whatever, but we see that that cancers themselves well know the structure. They both came to the yes.
Other questions, comments?
Yes, I have one question.
Please.
You have one scientist from Russia, the son. Can you tell me please the institution of
His
the
institution,
Yeah.
Institute of Mechanic.
Institute of Mechanics?
Yes.
Where is this?
In Petersburg.
Moscow?
In Petersburg. In Petersburg. Sound Petersburg.
Where is this?
In Petersburg.
In Moscow?
In Petersburg.
Okay.
Yes, I found it very short. St. Petersburg. This is St. Petersburg. Yes. No difficult question.
If there are other comments or questions? If not, so thank you again.
Thank you for your question.
All helps was devoted to some problems in practical modeling in biology, medicine, and raising a lot of questions. I hope a little bit it is already some effect they see. And now it's coffee break.
like, this is my template.
Do I change the slides from here?
The arrows.
And from here?
Yes, the arrows.
time for our second afternoon session. Next speaker is Maria Verati from National and Christian University of Athens. Please.
Thank you very much. Thank you for the invitation to this meeting. It's an honor to be a speaker here, representing Greek women in mathematics in actually two ways. One is because I'm the only Greek speaker in the program. The second is I want to show, sorry, not this arrow, none of the arrows actually. Big spoiler. So these are or click. Okay, now it works. Okay. Okay, so a couple of years ago, with some other academics in Greece, we founded and we are running now an association, Greek Women in Mathematics, like trying to imitate all the other very famous organizations. So we started a couple of years ago, and we are trying to organize some activities. Like, okay, on our website we do have some job offers, but mostly it's we've organized a workshop which was very successful, and now we're going to do a second one next summer. A series of podcasts. They are in Greek language, but we're gonna also add English subtitles, so this is gonna be a work in progress. We're starting soon a mentoring program, so we see that there was a lot of women asking for it, so they came to the workshop and there was a big symposium about it. So you're also welcome to join us. Even though, as I say, well, the Greek language might be an obstacle, but we're trying to work this out. And also, please feel free to talk to me if you're thinking about maybe starting a collaboration between or organizing an activity between Greece and one of your countries. So I'm going to talk to you about my research in mathematics. So there will be no medicine. There will be, actually I'm doing pure mathematics. I'm an algebraist. I'm doing representation theory, so there will be maybe a very, very brief mention of applications, but it's going to be a bit different from the previous two talks. So I'm going to try to show you a bit about problems open in representation theory of finite groups. And I'd like to start this talk about representation theory with a joke from the Big Bang theory. So at some point, Sheldon goes to this, I don't know, waiting room, and they have water with cucumber in it. And he says that, wow, they mixed the most boring beverage with the most boring vegetable, and the result is just, yeah, that's what he's doing. And so in this talk, we're gonna mix very simple theories, like we're gonna mix linear algebra, which is like the first type of algebra we see at the university, and with the symmetric group, which is the first group we learn in group theory, well, besides abelian groups maybe, like cyclic groups, but like the first non-abelian group, you see? And we're gonna see that it's not a disgusting thing, but it is very complicated still. Like, even though we take like the first and still there are many things that are unknown. So we're going to start with a bit of the history of the subject. So it starts also with a letter, because we saw in the Vostok there was also a letter between two famous mathematicians, Dedekind and Frobenius. So Dedekind, both German, wrote, he had this problem in his mind that he was trying examples. Well, it's not very important to read all of it, but he said, okay, let's take 10 the multiplication table of a group, turned it into a matrix, and then he noticed that the determinant of this matrix factors in the product of irreducible polynomials in the variables, each of which occurs with multiplicity equal to this degree. So he noticed a pattern, and he said, in all the examples I'm doing, I cannot, like, it works like that, but I don't see a reason, and and he wrote to Frobenius to see if there is an explanation about it. So Frobenius saw this as an exercise, an opportunity, and this led him to generalize what is known the theory of characters for finite groups. Actually, he didn't develop it. Characters were known for only abelian groups at that point, like groups where everything commutes. Works, I think it's back to Gauss. But he is the father of the theory of characters in general, and he also says this thing, which was actually foreshadowing, that he wants to develop this notion in this letter, since I believe that by this introduction, group theory should undergo a major advancement and enrichment. And this is actually what happened. So he did solve later on actually he proved what the kid asked him, but to do this, he actually developed what is known nowadays as representation theory of finite groups. So how representation theory works when it comes to finite groups, you take your finite group, your favorite finite group, and we work over a field, I say algebraically closed, think of the complex numbers, and you have a dimension, a vector space, a finite dimensional. So a representation will be a group homomorphism from the finite group to the general linear space of V. So we call this representation theory because every element of the group is represented by actually what is a matrix. So it's a linear, an invertible matrix, because the elements are invertible in the group, so you want the matrix to be invertible. And this is what's called a representation. So the idea is, instead of working with the group elements, we're going to work with matrices, because matrices we do understand better, and we have tools from linear algebra, and this is where linear algebra comes in, to study the matrices now, not the group elements anymore. And through the group homomorphism, we're going to go back and forth. And the characters I mentioned on the previous slides are just the traces of the matrices. So the trace of the matrix gives us what we call the character of the element, and then we have a function from G to K which sends every element to its character. And it's called a character because it turns out that it characterizes very much the representation. So it's enough to study the traces. Okay, there is some information lost, but they characterize in a big degree the representation. And for example, a key of 1 is, so the identity element goes to the identity matrix, and so Q1 will be just the dimension of the vector space. We will say that V is an irreducible representation if we cannot find a smaller representation inside it. So there is no non-trivial sub-representation. And we know that if we're working over C, so in characteristic 0, that's why here I said algebraically closed field, because it's not necessary that it's characteristic 0. We know that every representation is a direct sum of irreducible ones, so we only study the irreducible representations. And when it comes, for example, to irreducible representations, we know that if the characters are the same, then the representations are isomorphic. So that's why we say it characterizes the representation. Remark for people who are familiar with algebraic vocabulary, but it's not necessary. It's that if you know what the group algebra is, so a group algebra is just formal sums, linear combinations of the elements of the group, then a representation is a module over the group algebra. But Otherwise, if you don't know the module vocabulary, just stick to the definition I gave you. It's only because later on I'm going to talk about representations of algebras, and this definition is the one that makes sense. But my talk is introductory, and you don't need to know everything to follow it. So let's go now to the symmetric group, because we're going to talk about that. So we know that the symmetric group is generated by transpositions. So a transposition will be I plus, so it's enough to generate by the transpositions exchanging 1 and 2, 2, 3, 3, 4, n minus 1 to n. So the transpositions Si, which permute I and I plus 1 and fix everything else. And our toy example will be S3, which is just generated by two transpositions, S1 and S2. And in this case, we have three irreducible representations. One is the trivial representation, where we send everything to 1. This kind of representation exists for any group. Any finite group, you can just send everything to 1. This will be a trivial representation. Another representation that it is a representation, and you know if you have done the course of the symmetric group, is the sign representation. So actually, we send every element in the group to its sign, which is -1 to the number of transpositions you need to write the element as a product of transpositions. So actually, every transposition is sent to -1, and then if you have a product of 2 transpositions, it's sent to 1, because you want this to be a group homomorphism. And the third one is a two-dimensional representation, and I'm just giving it here. It's not as direct as the others. We take this subspace of C3, the one generated by actually these are the elements where the sum of coordinates is equal to 0. It's generated by these two basis elements, and then we can show that these matrices actually give a representation. One can tell me, well, then just why not take C3 and just have the symmetric group permute the variables. This is indeed a representation. It's a 3-dimensional one because you're working over C3, but it's not irreducible. It's not irreducible, and this is why this V appears. You can break it into this, and actually this S3, if you permute, it actually stabilizes the subspaces where X is equal to Y is equal to Z, because when you, and this, there it acts trivially on this. So you have the trivial representation and the other one. So it is a representation, but not an irreducible one. So how do we know that we have found everything? So one, there are many criteria. For example, okay, sorry, this was not the time for the criteria. So the other thing I wanted to say was that one can see S3, can see it as the group of symmetries of an equilateral triangle, so that they have 6 elements here, and then each we can see each its transposition as a reflection through with this axis of symmetry. So then S1, so for example, okay, we don't have the colors, but then I can see S1 to be the reflection with respect to this axis, and S2 with respect to the red axis. And then I could use the standard matrices that we're used to do when we're doing reflection, with the cosinus and the minus sinus on the other side. And we see that I can use different matrices here, but if you see the traces will be 0, and the traces here are 0, and actually we can show that this is actually the same representation. That's why I call it the reflection representation, because it corresponds to this kind of reflections. So now, how do we know that we're done? Okay, for example, we have this. There are many formulas. One tells us that if you take all irreducible representations and you take their dimensions to the square, you have to find the order of the group. So here we have 1 plus 1 plus 4, so it's 6, so we are done, there's nothing else. And now the result, which is very specific to the symmetric group, is that the irreducible representations are labeled, are parameterized by the partitions of n. That is how you can write n as a sum of positive integers, where it's a decreasing sequence of positive integers. So in this particular toy example, how do you write 3 as a sum of positive integers decreasing? So it's either 3 or 1, 1, 1 or 2, 1. So we have 3 partitions of 3, so you have 3 reducible representations. And there are actual formulas of how you can describe the elements, the matrices, using the partition. So there is combinatorics involved. When you do the representation theory of the symmetric group and you use the partition approach, you have combinatorics involved. So now, as I said, this works in characteristic 0. So if you work over the complex numbers. So, however, you could take your field to be of positive characteristics. That's the other case. And in this case, we know that things, so I mentioned before the group algebra. So in the previous case, the algebra, characteristic 0, the algebra is semi-simple. So the scenario that I showed you is when the algebra is semi-simple. And this happens when P, the characteristic, does not divide the order of the group. So even if you're in characteristic P and it does not divide the order of the group, the representation theory will work as in characteristic 0. So this is the good case, P not dividing the characteristic, P not dividing the order of the group. However, when P divides the order of the group, we have what we call the modular representation theory. And this was developed by another German mathematician, Richard Brouwer, much later than Frobenius. And what he came up with was the theory of decomposition matrices. So, in characteristic P, you don't do what you do in characteristic 0. So you don't start trying to understand the irreducible representations from scratch. What you do is you try to see what happens with the irreducible representations you had in characteristic 0, what happens to them when you change the characteristic. And then you have a matrix where the rows are labeled by the reducibles in characteristic 0 and the columns by the reducibles in the new characteristic, and you see very roughly what happens to the irreducible representation you had before. How they break into irreducibles now. So if here you have a 1 and a 1 and zeros, it means that the irreducible you had here just broke into a sum of 2 new ones. If it's a 1 and then you have all zeros and all zeros there, it means that it still remains irreducible and projective. So I'm hiding some things under the carpet here, but the idea is this: you get decomposition matrices, and what you get, if you organize the matrix into a block form, you can always do that. Maybe it's a big block, or the idea is if you have zeros, everything else. That's what we call the block of the algebra, the blocks of the algebra. And we say that 2 representations here, or 2 characters here, are in the same block if they label rows in the same smaller block. So you organize it like that. You can always do that. And for example, we have a criterion that a character, an irreducible one, will be alone in its block, so you will have 1 and zeros everywhere, in the row, in the column, if and only if P does not divide this number. So it's the order of the group dividing the dimension. We know that this is always an integer. So I said there are many formulas known about representations. For example, we know that the dimension will always divide the order of the group. So there are many criteria like this, and this is called the sure element of K. So for example, you see immediately that in order, if P does not divide the order of the group, you will have that even for the, it will mean that P does not divide any of these numbers. So you will have the identity matrix. So the representation theory remains the same. So the name Schur comes from Isai Schur, who was the PhD advisor of Richard Brouwer. And actually, he was the only student of Frobenius who worked on representation theory. So Frobenius started representation theory, and he had many PhD students, but only one of them worked on this subject. So he's so famous about this area, but he only gave this topic to one of his students. Then Schur supervised many students on the topic. One of them was Richard Brouwer. So the decomposition matrix of the symmetric is not known. So that's why I said the first group that comes to mind when you do finite groups, we don't know what happens when we know what happens in characteristic 0, but we don't know what happens in characteristic P. So it's not known in general. So there's no formula for what the entries of the decomposition matrix are. We do know things because it's like maybe, for me surely, but maybe the biggest open problem in the representation theory of finite groups would be we don't know yet the decomposition matrix of a symmetric group. Of course, of other groups as well, but like we don't even know that. But we know things. There's a lot of research on the topic. It's big motivation for people working there. So, for example, we know that the decomposition matrix has this nice unitriangular form. So you have these ones. It's not square, but there will be ones in this quasi-diagonal and zeros on top, which makes us like the nicest. If the decomposition matrix has a nice form, we learn a lot of things about the irreducible representations in this non-semi-simple case. Also, we know that the number of columns is equal and parameterized at what we call the p-regular partitions of E, and that is the partitions where you don't have a part repeating more than p times. So, for example, for n equals 3, the bad prime numbers are 2 and 3 because they divide 6. And in this case, this partition 1, 1, 1 is not too regular because we have a part which is repeated more than 2 times and more than 3 times. Well, greater than or equal to 2 and 3. So in these two cases, we have two symbols. 1, 1, 1 is not. I will have 2 columns and 3 rows in the decomposition matrix. I give the example. For example, for p equals 2, the decomposition matrix looks like that. So this is one block, actually. I wrote it like this to have this nice form. And this is alone in its block. And this, we expect it to be thus, because here the Schur element is 3, so it's not divided by 2. While here the Schur element is 6, so it's divided by 2. While in the case for p equals 3, the decomposition matrix looks like this. So we have a big block, everything is inside, which makes sense because the Schur element is divided by 3 in all cases. So my area of expertise is a representation theory of what we call Ivahori-Hecke algebras. So what is this? In the case of the symmetric group, we have this kind of presentation. So we can present it by generators and relations, and these are the generators are the transpositions, and these are the relations. So we call the first ones, we call them Brady relations, and then everything else is of order 2. Every generator is of order 2. Now, the Ivahori-Hecke algebra is an algebra over this Laurent polynomial ring where Q is an indeterminate. And the difference with the presentation of the symmetric group is that the generators are no longer of order 2, but they satisfy this quadratic relation. So that's the only difference. And now we can observe that if we take Q to be equal to 1, we recover the symmetric group, but otherwise it's something more general than that. And we know that in this case, in the case that this algebra is semi-simple, which means that the representation theory will look as the representation theory of the symmetric group with characteristic 0. So the reducible representations, as I said, algebras have representations as well. They are in bijection with the partitions of N. So what's the modular representation theory scenario in this case? It's not when we go to positive characteristic, but it's when we specialize Q to a root of unity. So if Q specializes to a primitive if root of unity, where E is not necessarily a prime number, we have again that the reducible representation are in bijection with the irregular partitions of N. So we have again a decomposition matrix. We know that the decomposition matrix looks as it should. So it has the same form as the decomposition matrix of the symmetric group. And we can compute it. That's the thing. I'm not saying what's arithmetic verification theorem, but there is a theorem which allows us to compute the decomposition matrix in this case. And there is a conjecture from 1990s that the decomposition matrix of the Fajori-Hecke algebra should be the same as the decomposition matrix of the symmetric group if you take eta to be a primitive pth root of unity where p is a prime number. This conjecture is wrong. So it was open until very recently, but a few years ago there was a work by Elias and Williamson where they proved many open and other open conjectures in the field, and they proved that this conjecture is not true. 2017, he found a character example for n equals 1,744,860. So you tell me, so the whole talk, okay, I'm telling you all this, and then I give you a reason why we look at Hecke algebras, and then I tell you that this reason is wrong. But before I tell you that this is not the reason we're looking at Hecke algebras, but this made for a very good starting point when writing a proposal, saying, you know, we're looking at this, there is James' conjecture. But I found this beautiful thing said by Geoff Robinson, who is also a representation theorist, about the ideas of conjecture. And there is, if a conjecture turns out to be false, it does not necessarily mean that work in that direction should cease. If that first approximation to the truth turned out not to be completely accurate, surely we can attempt to try a better approximation, while when a theorem is proven, then that's it. So I found this very inspiring, so that we shouldn't discard, okay, conjecture is wrong, so just drop it. There is maybe a reason why it was true until 1 million something. It could be that there are some cases why it's true in certain cases, why it's not true elsewhere. But the Hecke algebras, the ones I'm working on, they did not arise to study the representation theory of the symmetric group. They arose in the study of other finite groups in the representation theory of groups of matrices. So GLN is the group of matrices, of invertible matrices with coefficients in the finite field FQ, where Q is a power of a prime number. SLN is the group of matrices with determinant equal to 1, and then you have the special orthogonal group. So these are finite groups of matrices. So when studying the representation theory of these groups, then to each of them we can associate what we call a Weil group. So this was work done in the 60s and 70s, and it was actually done even earlier by number theorists, but working not over finite fields, but working over what we call p-adic fields. So to each group like this, we associate a finite group, which is called the Weil group. For example, for GLN, this is the symmetric group. And then to this Weil group, we associate a Fajori-Hecke algebra. And then this little Q that we saw in the Hecke algebra becomes the Q of the field. So they showed that we can understand the representation theory of these groups by studying the representation theory of the Hecke algebra, and we don't need to treat differently these Q's. So if Q is equal to 3 and Q equals to 2, it's not that different because we work on the Hecke algebra HQ, and Q can be anything. So this is where the theory of Hecke algebra started. So these are, this is the type of Weyl groups we can have. So there's a classification of Weyl groups. So you have the symmetric group. This is the type A. This is type B and type D. So these are just generalizations of the symmetric group. And then you have some exceptional groups, E6, E7, E8, F4, and G2. And these all are reflection groups. So that's why before I gave the definition, I gave the example of S3 and said, you see, this can be seen as the symmetry group of the equilateral triangle. It's because the symmetric group is actually a reflection group. And here I will give you a more general definition. So you take a complex vector space. We say that an element, a linear map from V to V is a pseudo-reflection if it's an element of finite order, and also it fixes a hyperplane. This is what I mean, dimension of the kernel. It means that if the vector space of dimension n, then this fixes a subspace of dimension n minus 1. So what's a usual reflection? So the idea is that if you see this in a matrix form, it will look like that, where eta is a root of unity. So in normal reflection, so a normal reflection, this eta is equal to -1. So a normal reflection, what we have in mind is that it fixes a hyperplane, and then you have a vector orthogonal to it, and it sends it to its opposite. We only don't call this reflections because people have in mind this as a reflection, while here theta can be another root of unity. So that's the generalization. And then the complex reflection group is a finite group generated by pseudo-reflections. And if we are, okay, the trace of all the elements belongs to R, so actually if you have real reflections, then we take a real reflection group, which is also known as a finite Coxeter group. While if all your matrices are in the rational numbers, so this is not only the traces of the generators, but the traces of all the elements, then you have the Weyl groups that we saw in the previous slide. We have a classification of all complex reflection groups. So we call it the irreducible ones in the sense that the reflection representation is irreducible. So every complex reflection group is a product of irreducible ones, so you cannot break it further. So we only classify these. So you either have a group of matrices which are parameterized by 3 numbers D, E, and N, or you have 34 exceptional groups. So the anecdote of why the groups have these numbers G4, G5, G6, G37, it's because Shepard and Todd, who did this classification in 1954, they actually had G1, G2, G3, G4, but then later on it was found out that G1, G2, G3 was already in the infinite series. But they kept the name, so it's G4 up to G37. Okay, so some examples. So GD1N, for example, is this group. We saw it as a Weyl group for D equals to 2. It's a generalization of the symmetric group. So, of course, in there we find all Weyl groups and all real reflection groups. This is type A, this is type B, this is type D. And also, we have the dihedral groups. Dihedral groups are the groups of symmetry of regular polygons. Of course, they will be in there. So these groups are real reflection groups, but they are not Weyl groups, except in the cases where except for the triangle, the square, and the hexagon. These are the only cases where it is indeed a Weyl group. But even cyclic groups are in here. So this group is the cyclic group of order D. So even finite cyclic groups are complex reflection groups. So reflection groups are very often referred to as groups of symmetries of objects because, okay, the groups of symmetries will be among the reflection groups. For example, for a cube, the symmetry group is, okay, it's the group of type B, G213. So if you write the cube like that, one could say that the complex reflection group, GD13, would correspond to the symmetry group of a complex cube. So one way to see complex reflection groups would be as the symmetry groups of objects in the complex space. The nice picture that I had in the beginning, this is, I put inside quotes that this is a symmetry group E8. So E8 is very famous. It became very famous. There were many magazines, like at some articles in magazines about E8. Okay, E8 is the biggest exceptional, even complex reflection group. So it's the biggest exceptional one. So it's the most difficult to do calculations with. Okay, so this is actually what we call the lattice of roots of this, because we study root systems. But if we say, I found that the reflection group is the symmetry group of the root system. Anyway, so this is not the object of which this is the symmetry group. But it's a very cool picture, and all the presentation theorists use it to see, okay, beautiful picture of what we do. But, okay, I didn't talk about roots, so I didn't explain what it is. So, species. This is what started me in research about the representation theory of Hecke algebra of complex reflection groups. So this is a funny thing for Greek people. So in 1993, there was a conference on the island of Spetses in Greece. And we saw that for these kinds of groups, the groups of matrices of a finite field, we have as associated by a group, and we can associate the Hecke algebra, and so on, and study them. So in 1993, there was this conference in Spetses, and Breuer and Riquet had this idea: what if we take W to be a complex reflection group? So maybe there is an object which generalizes the groups of matrices, and which has as value group a complex reflection group. And that they called it the spets. One spets, and the plural is spetses. So for Greeks, it's very funny that there is a mathematical object called spetses, but it's called, and then there are spetial specialization. They like very much this word. They define the Hecke algebra of a complex reflection group. So motivated by this, they developed the representation theory of this object. This object has yet not been found. There has not been a single example. We don't know if it exists. I won't lie to you. I was giving this talk, when I started my PhD, that was 20 years ago, I was very much into this, and people were like, yeah, surely it is this. Everything works perfectly. Everything works exactly as in the real case. But 30 years later, and still haven't found a single example. So people are quite disappointed now. But still, that's why I called this, like my PhD advisor was Michel Bouet, and he liked to talk about miracles. So, and a miracle. This works perfectly, as in the real case, and a miracle. So, is there an explanation behind the miracle? Like, is there an object that controls all this? Like, is there a reason, or are all these miracles? It just happens that all the theory falls perfectly into place for complex reflection groups with no explanation, however. It just works. So they came out with two big conjectures. The other thing was that they were seeing that everything works perfectly, like miraculously, everything worked fine, but it was very difficult to prove. As I said, Spetses is still open. Nobody has found it. This thing that I'm writing here, which is more technical, but I'm close to the end of my talk, is the Breuer-Riquet-Freynes conjecture. They said that the Hecke algebra is a free module of rank, like a vector space. If you don't know what a module is, see of it as a vector space of dimension equal to the order of the group. This thing was known in the real case. Very easy, quite straightforward proof. For the things to work, for the theory to work, they had to have this. So they assumed it. This conjecture remained open for, it was proved in 2018. So it remained open for like 25 years. But it's now a theorem. So it's proved, it's called the conjecture because it was a conjecture for 25 years. But many people worked on it. And there is a proof for the groups of the infinite series, which is combinatorial one. And then people worked computationally, case by case, using a computer to do all the others. This is another annoying fact about complex reflection groups, is that in the real case, everything is proved nicely and uniformly. And in the complex case, the same result is true, but you do it every case separately, and we don't seem to find a proof that works for all groups. But this is a general problem in finite groups, is that many things that are nice and very easy to state, they have proofs where it's, in this case, the proof is like that. In this case, the proof is like that. And the result is always true, but the proof is case by case. The other is this conjecture, the Bruemal, which turns into, I mentioned at some point sure elements, and the reason I did mention it back then is to tell you that there is a form of sure elements which control the block theory for Hecke algebras in this case. This is still open, and actually, okay, we worked on this with many Greek mathematicians. So, okay, GDEM was already known by Brem, Kemal, and Mataz. Then there were these cases by Mal and Michel, which are the easiest to deal with computationally. And for these groups, we actually worked, Christina Bura is a cryptologist. So we got this idea that, okay, it's a computational problem, maybe we should turn to somebody who's a computer scientist. So we worked with her, like with Irini Habli, so he helped us also with the programming, and we are doing pure math, so we know some programming, but actually it was a joint collaboration between computer scientists and us to prove the conjecture in some cases. But then our cryptologists found that this was the longest project ever, and we found that it was very short for mathematics. So we realized that we had very different ideas of how long the project is. So we did 6 months for this. For us, that's a very short proof. For her, it's like, I've never worked on a single project for 6 months. So it was a very, we learned many things. And she also thought that the computer could do everything, and we were amazed that the computer could do so much. So she was shocked to find out that the computer couldn't solve this. There was a lot of human factor. There were a lot of things that we did by hand because the computer was turning in loops, and we had to get in and tell it, okay, you're not gonna do this thing, you're gonna do the other thing. So a lesson for her, but we were amazed at how much pure mathematics stuff it could do. So big lesson, this collaboration. And this is where I'm gonna tell about, so Hecke algebras have also lots of other applications. So I mentioned the ones in representation theory, but then they turned out everywhere, like the one of complex reflection groups. The ones that they developed motivated by Spetzes, they started showing up in many things. They showed up in geometry, or these are Calogero or Moser spaces. They have in dynamical systems. They show up there in the symplectic resolutions. I'm not going to talk a lot about that, but so complex reflection groups show up there, and it's a big thing. In the definition of knot invariants, so knots are knots and links are topological objects. There is a way we can see circles in the 3-dimensional. It's embedding of circles or collections of circles in the 3-dimensional space. So Jones in the 80s used a trace function on the Hecke algebra of the symmetric group, which gave rise to a famous polynomial invariance of knots. So knot invariants allow us to distinguish knots and links which are not the same. And then for complex reflection groups, Sofia Lamborghini, mostly Michael Keck, used them, the Hecke algebra of complex reflection groups, to compute invariance in the solid torus. And this is the only part where there are applications I know in biology, because knots appear in the in proteins and also in the structure of the DNA. So they're using these results. So there is Hecke algebra, not theory, applications to biology. Quantum groups, also a field of study in representation theory, which came later than Hecke algebras, but also Hecke algebras of complex reflection groups show there. So there are connections with theoretical physics I know less of, but I am in projects with people who are actually doing physics and they're using these kinds of algebras. So it all started theoretically through an idea motivated by a non-existent object, and it turned out lots of applications in different areas. So the last thing I want you to leave with this impression is I always heard that working on finite groups, people who are not doing finite groups, they assume that because it's finite, everything must be known, because it's finite. You do everything and you're done. So the answer is no. Many, many open questions here. So thank you very much.
Any questions?
Well, just naive. Can you, in 2 minutes, explain connection what exactly the one you skipped to the root system, and what are they, how they connected to this reflection while groups, right?
Okay, so it's that. So this is a way we study the reflection groups. Like it's through their reflection action on the vector space. And then the vector space we take, so it's, well, if I would say simplest way, so you take some elements in this vector space which are called the roots. And then inside there, it's like a basis of the vector space is what we call the simple roots. And so these simple roots will give you the generators of the group afterwards. So it's every root will correspond, every reflection will correspond to which, there is a characterization of its reflection by which vector it sends to its opposite. Because you send it to its opposite and you fix the hyperplane orthogonal to it. So this will be the root of the corresponding reflection. And then you have the simple roots giving you the generators of the reflection group. So there is this connection.
Does it mean the group will correspond to some lattice somehow generated by these vectors? No? Some lattice
yes.
vector space?
Yes, it's a lattice. All the roots will form a lattice. And then you have the Weil groups are also called, for example, crystallographic groups because these are crystallographic lattices, the one appearing for this kind of groups, the Weil group, but then you have, and then if you just write down all the roots, you get pictures. So, for example, for the S3, it's something simple. It will be like, now I don't have, it will be just 6 vectors. I mean, it will be small vectors, but like E8 that I showed, it acts on an 8th dimensional space. So you see S3, it acts on a 2-dimensional space. I can draw the roots. So this thing, which it's a way to write on paper the 8th dimensional space and the elements. So I don't know if this answers a bit, gives an idea.
Very good, thank you.
Any other questions or remarks?
If we start, but it's also just naive, complex, but if it's reflection of something high like quaternionic or something, reflections in quaternions or something, this has been, or is it meaningless? Well, if we have real, we have complex reflections.
Yeah.
We should have something like quaternionic reflections.
Okay. I don't know, maybe, I don't know.
It's non-commutative, so it may be completely
And for example, we do finite. There are people who are doing infinite reflection groups. So why restrict? We are doing finite, like in definition, we say a complex reflection group is a finite group. And then people say, why not take infinite one? So maybe there are other generalizations possible.
Other questions? If not, let's take the end. demonstrating miracles. It's time to some little break now, 10 minutes break.
Yeah, I know how it's very far, like this representation here, it's very different from the representation here of this one, right? So it's very completely different groups. I know it's very geometrical.
Yes, you use them together.
I will show you.
Yeah, when I go to the presentation, gives them to me. It's on the left of the end. It's huge. You can walk in. Place it. So and what I do is more about case competition in classes, also literature. That they actually, I have some
1 and the minus 1. And this is the next step from minus 1
I just came earlier from my home.
We continue with the next speaker, Elena Kadjeva from University of Information Science and Technology from Malta. It's the talk. Her talk is Aesthetic Charms of Mathematics. Please, Professor Kadjeva.
Thank you. I would also like to thank the organizers for the organization and for invitation. I already met colleagues with which I hope we can cooperate, and there's still time to make new friendships and collaborations. So this talk is a kind of popular talk. It will be different than these theoretical mathematical talks, and applied, not only theoretical. I was inspired to look at aesthetic charms of mathematics by two things. The first one was it was how to say, maybe curiosity-driven research of how mathematics was defined through centuries, and there were so pleasing definitions that were, I mean, maybe I cannot say definitions, but descriptions of the term mathematics, which were comparing mathematics to supreme beauty or God's creation or ultimate truth, and I wanted to get deeper into that perspective of mathematics, which actually give rise to another aspect of mathematics, how beautiful it is, how elegant it is. It's not only elegant when you're meeting some mathematical content which is reflected in some equality or in some proof, equality like Euler's equality, which says that E2 I pi equals to -1 connects these four constants. But I wanted also to go in the direction of the beauties where mathematics and art meet. Art reflected in paintings, in music, or in design, some more modern art. So that was one of the reasons, and the other one was, I mean, probably we are all facing nowadays with students which are with low attention, with low focus, with maybe low patience, because they're actually they have grown up with technology and they need immediacy, they need some interesting things to keep their attention, and mathematics is not that kind of field. It is systematized, structured knowledge for which it is important to have its abstractness understood, not only application, its order of all mathematical concepts is important, and we can't always be fun. I mean, we can't always be interesting for our students if we want to precisely convey mathematical concepts. So I thought, is there a way to keep their attention pointing out the mathematical beauties, not only the mathematical preciseness and strictness in the mathematical content. So those were the two reasons, and I will first start with the descriptions of mathematics. So, okay, let me first go to the outline. The first comes the motivation and different descriptions of mathematics, and then the aesthetical charms reflected in mathematics and music, painting, photography, design, and face beauty as well as the last curiosity. So as we know from our students, most of them, I work with engineering students, not all of them are interested in mathematics, although they should be. But that's the reality. And they always consider cold and austere abstract science, which they are not sure whether they will need or not. So I mentioned about this challenge. So we are really, as teachers, we are in front of, we are facing that challenge to keep their attention while keeping the strict mathematical structure of our classes, and to explain to them that mathematics is not only a tool for problem solving, but it's, as our academician said, a queen of sciences, and it's important base of any research. I mentioned this perception of mathematics throughout history, which lasts more than 2,000 years, and comparison to poetry, supreme beauty, harmony, order, law, ultimate truth, work of art, God's creation. And it's understandable why these comparisons are made when one takes into account that mathematics and philosophy were very close fields for a long time. And what will be the effect of including these mathematical beauties in a class? Maybe it can inspire creativity and a deeper appreciation to both mathematics and these art fields. So there are different definitions who explain the word mathematics. Dictionary definitions, which have further divisions in mathematics and general dictionaries, and working definitions, which can be further divided in scientific and non-scientific. And these non-scientific actually were those that were most interesting to me. And I will I will focus my talk there. So in general, I will not read them all, maybe 2 per slide. In a general dictionary definition that are taken either from dictionaries or from encyclopedias, mathematics is defined as, let's say, from Cambridge, the study of numbers, shapes, and space using reason, and usually a special system of symbols and rules for organizing them. Or from Merriam-Webster dictionary, it is defined as science of numbers and their operations, interrelations, combinations, generalizations, and abstractions, and configurations of space and their structure, measurement, transformations, and generalizations. There are other definitions, but there are also dictionaries that do not define the word mathematics. It's not often defined because there is no particular definition. It's, or I can say maybe not definition upon which mathematicians and linguists agree. in mathematical dictionaries, some of these dictionaries, like the first one, are for children. So for children, we have that simple and short definition: the study of shapes and other entities by logical means. Or we have Oxford Concise Dictionary of Mathematics, the branch of human inquiry involving the study of numbers, quantities, data, shape, and space, and their relationship, especially their generalizations and abstractions, and their applications to situations in the real world. So not many emphasize the application of the field, but they most, because if you analyze the definitions, there are some who emphasize the abstractness and some who emphasize the applications, but most of them deal with abstractness of mathematics. And then we have scientific working definitions. Let's go with the first one. Mathematics is a science devoted to the exploration of number, quantity, geometry, and in modern times also includes investigation into yet more abstract concepts of order and into analogous types of purely logical relations. Or let's go with the Russell's definition. Mathematics is the science of number and space. It starts from a group of self-evident truths and by infallible deduction arrives at incontestable conclusions. The facts of mathematics are absolute, unalterable, and eternal truths. So, in many cases, the description of mathematics depends on personal perspective, sometimes on institutional perspective. Of course, at the period in history when that was generated, that description, maybe from the target audience, but having this set of descriptions actually gives all the different approaches how can one understand mathematics. And these are the list of non-scientific working definitions follows. Some of them are grouped as philosophical, like this list. From Bacon, mathematics is the door and the key to the sciences. Or from Dirac, mathematics is a tool specially suited for dealing with abstract concepts of any kind, and there is no limit to its power in this field. And I really feel that mathematics is limitless, no limit of its power. I also like this from Young Stewart. Formal mathematics is like spelling and grammar, a matter of the correct application of local rules. Meaningful mathematics is like journalism. It tells an interesting story. Unlike some journalism, the story has to be true. The best mathematics is like literature. It brings a story to life before your eyes and involves you in it intellectually and emotionally. All of us, we are intellectually involved in mathematics and sometimes also emotionally, because we feel good emotions when we come to some interesting or elegant mathematical concept. And we have a group of aesthetical non-scientific definitions. Okay, I will go with Archimedes. Mathematics reveals its secrets only to those who approach it with pure love for its own beauty. I like this very much. Also, the fourth one from Quran, mathematics is an expression of the human mind. As an expression of the human mind reflects the active will, the contemplative reason, and the desire for aesthetic perfection. I also like this expression, aesthetic perfection. Its basic elements are logic and intuition, analysis and construction, generality and individuality. Then then we have a static or creative definition. So here is the sentence that mathematics is compared to poetry from Einstein. Einstein's quote, "Mathematics is in its way the poetry of logical ideas." I also like this expression, poetry of logical ideas. Or the fourth one from Russell, "The pure mathematician, like the musician, is a free creator of his world of ordered beauty." And so on. Then there are social and humoristic. For example, the first one from Descartes, "Mathematics is a more powerful instrument of knowledge than any other that has been bequeathed to us by human agency." And the last one also from Russell, which belongs to the group of humoristic, "Mathematics is the subject in which we do not know what we are talking about or whether what we say is true." So probably, I couldn't understand this point of view when I came to his quote, but probably he was addressing to some specific audience because otherwise it would have no sense, because we actually know what we are talking about as mathematicians, and okay, whether something is true or not, it should be proved, but we usually know, or we would say this haven't been proved yet. So I put the specific words in clouds. The first cloud is from dictionary definitions. They most mention the words number, shape, space, measurement, quantities, relations, symbols, structure, order, rules, and also from mathematical dictionaries, abstraction, generalization, application, words that describe mathematics as a term. And then we have this scientific working definition, which beside these words additionally describe mathematics with deduction, deductive reasoning, analogy, assumption, postulates, axioms, theory, abstraction, exploration, experimentation, empirics, and application. And here, the words that I liked very much, and they do have something in common with aesthetic charms of mathematics: greatest forms of beautiful, supreme beauty, ordered beauty, pure love, intellectual and emotional involvement, phenomenal world, creative theory, key to the universe, aesthetic perfection, the poetry of logical ideas, a poetic form of truth, creation of the human spirit, and emperor of the whole world. So I will now try to, all of these views that were mentioned, I will try to give you examples where it can be seen. So the first example is related to Fibonacci sequence, defined recursively, so with first elements 1 and 1, and every next is the sum of the previous two. And how a music can be created not only from Fibonacci sequence, but from any sequence, if the digits are assigned to particular keys on a keyboard, and if you have a musician who can arrange those, digits that are generated from the Fibonacci sequence, can convert into music, a very nice melody can be generated. Just a second, I prepared a video of this. We didn't check the sound, but yes, 2.5 minutes.
The numbers in the sequence have extraordinary mathematical properties and can be found in patterns all throughout nature. So I decided to see what they would sound like as music. To create
Sorry. I didn't stop.
Music can be created using different linear transformations, so if you have one motif, then you can do translation, horizontal, or vertical translation, or transposition, or reflection, and so on. I have another video, but if we have time. And it wasn't so pleasant music as the first one. If we have time, we will play that one. So, and it is used, I think Beethoven has used these linear transformations. Then we are at connection between mathematics and design, and there the golden ratio plays important part. So, as an irrational number, it is defined either through limit of not the Fibonacci sequence, but the ratio of Fibonacci elements fn plus 1 over fn. That limit is exactly phi, or from golden rectangle, that rectangle whose longer side over the shorter side is equal to, A over B. This comes from one paper of ours with a colleague of mine who is in digital arts, and he makes designs. It was a concept of involving this golden ratio when students in high school are learning about irrational number, again to make their classes more liveful, more tangible with the real world, more tangible, more connected with the real world. But not phi exactly, it's approximations obtained by the first 10 terms. So the most used approximation of phi is just this last one, 1.618, but also sometimes as 1.5 as all these rational approximations are used because, of course, in reality you can't use the value of phi, you must use the approximations. And at which logos is this golden ratio or golden rectangle used? So it's in Twitter's logo. The diameters of these circles follow golden ratio. Then National Geographic logo, so simple. Yes, we have that ratio 1.618 divided by 1 of the sides of the rectangle. Then Chevron Energetic Company, then BP British Petroleum, and this design, I was surprised that it was sold for $221 million. Because it's about concentric circles which follow this, whose radiuses are following the Fibonacci sequence. Then Pepsi has included again the radius that follow Fibonacci sequence, and Toyota is within that rectangle with the same ratio. Here is also one image that depicts the design of Apple company, and Twitter as well, the same one, maybe more precise description, and two others. I'm not sure what are the companies that follow the Fibonacci sequence of diameters. And there are some new designs, newly developed designs for some usually graphic design companies, logos of such companies. And there is, I mean, not only from Da Vinci we know his concept that he uses golden ratio, but also from Johannes Vermeer, the girl with pearl earring. So this golden spiral is also used to describe or to point out what the main message that the author wants to send. For example, here the emphasis is put on the eye of the lady, and there on maybe on the smile of Mona Lisa. And I also put Kandinsky's art. He's one of my favorite artists. He paints geometric forms, paying attention to the balance and harmony in his paintings. For example, this is the motif of circles in a circle, and he also paints parallel lines or relations between lines and circles. So we have intersections both in the left and right part, and also he has involved golden ratio in his paintings as well. And what I want to say else? Also right angles and so normal lines, parallel lines. Escher, I don't know if you within art, but he depicts different paradoxes. For example, on this left image, it's called waterfall. So you have the feeling that water drops from this higher level to the lower level. But then if you follow the water, it seems like it's in one plane. And actually this is perpetuum mobile. The same water goes there. And he's really mathematically precise in his, these are not paintings, but they might be called prints, or there was another word, or relativity to the right. So if you observe the stairs and the walls and the doors, at one moment you will be lost what is vertical, what is horizontal. So he's a master of drawing illusions, of depicting Euclidean and non-Euclidean space. And I have two more from him. So here he has drawn like distorted space, but it's very successful. Every line, and again illusion, because this painting which is observed is simply continues to the scenery of some city. And then the right one is called day and night, because you may observe maybe white birds that are up in nighttime that are heading in that direction, but also you may observe blackbirds during the day that are directing towards this direction. And that transition from the floor tiling to birds is also interesting. He has also painted the Mobius strip and Klein's bottle, but I don't have, I just made some choice of his paintings. Mathematics and composition, this is interesting. I mean, composition is important arrangement in cinematography and photography. So it's important how you will arrange the elements in a frame in order to convey some message, what will be emphasized, what shapes you will include, what patterns, colors, and so on. And that's the way how artists try to capture the audience attention, and how they attract the focus of the audience on some particular thing. The golden ratio provides a basis for some compositional techniques. The first thing is in photography. So golden points, or making figure eight in a frame, will give points which actually should attract the focus of the observer. For example, I mean, all of these intersections should bring the main message, and the eyes of this child are exactly at that one of the points of the grid, and also the whole concept in the middle rectangle is the main message in this photo. These are original photos from the co-author of that paper related to the composition in photography and cinematography. This is a scenery of a movie. A lady is reading. By the way, this is Geoffrey Blake. This is our famous actress. And again, the golden spiral used, and exactly the center of the spiral is in her eyes, and the main thing is captured in the spiral, the main message of this. And there is a rule of thirds which is very similar like the figure eight rule. So there is a grid, but here it is divided in thirds, and again the eye is that vertex, and the fingertips are in the other one. So I mean, I don't always fully understand the art, but simply I feel the pleasure when experience it. And there is some, I mean, emphasis of the human beauty related to the golden ratio. You know those Da Vinci's rules for, I mean, for sketching or for painting a human. So golden ratio is involved in our ratio of the body elements. For example, the full height divided by this should be, I mean, it's ideal if it is in golden ratio, but there are also such 1.618 ratio in the facial composition, how to say so. This length divided by this length is equal to this length divided by this length, and so on. And as people invent many things, they invented beauty according to the golden ratio. So in 2022, this was the last competition for beauty according to the golden ratio, and two actors, actually actress and actor, got that title of Miss and Mr. Golden Ratio Beautiful Lady and Man. And I was saying a joke once, if you ask a mathematician if he sees a beautiful lady, he might not like her because she's not after the golden ratio or proportion. Okay, so this exists, such election of face for now only on face beauty, not they haven't invented a competition for body beauty according to the golden ratio. And yes, I added here that this presentation is based on actually two papers. One was it was a review paper on the definitions of the term mathematics, and the other was a mathematical concept in lens-based media with my colleague, which is an artist, and he was interested. I mean, we simply joined our interest in this. And there was a presentation, Mathematics is Lovely, which was presented this year. So when I was invited by Professor Milusheva, I thought, because I wasn't sure about the audience, it's my first time here, I didn't know how it goes, and I thought it may be some popular talk with these aesthetic charms of mathematics. So I made some changes of that earlier presentation. So it's better to say not conclusions, but maybe summary. Want a summary here. I hope that I depict some beauties that you were not aware of in mathematics, and I will be happy if I inspire you to find further mathematical beauties, because after facing some of this beautiful mathematical content, I started to notice mathematical beauties everywhere. I hope that you will be also inspired. And okay, we mentioned some definitions, which my plan is from time to time to mention to our students. Let's see if I change their perception for mathematics. I'm not hoping much, but let's try. Yes, and how to involve some of the mathematical concepts. We can, we as mathematicians, from time to time, I think that we can spend maybe even 5 minutes a week or 5 minutes in 2 weeks to give them something different, because it's really, actually, as I'm trying, I don't think that anything is successful with these students. Maybe 10% of the students will be happy with giving different approach in the mathematical content, but from time to time, I hope that changing, just for changing the approach from the strict mathematical and rigid, which has to be like that, because no content should spoil the mathematical correctness. It's always, for no cost, because in primary school and high school they're trying to be fun, to be interesting, but to present everything with some pictures, with some simplified definitions, but then the mathematical idea can be spoiled, the preciseness can be spoiled. So not at the cost of mathematical preciseness, but some concepts might be connected with either with real problems or with some just beauties. It's just as art is, as poetry is beautiful, we could add some content alike in class. Yes, I also express this opinion that with such an approach, interdisciplinarity, cross-disciplinarity, or integrated teaching can be supported. And okay, golden ratio is influential mathematical principles that artists have employed because it provides a basis for many compositional techniques. Of course, artists are not, they never strictly follow some rule. They are artists, they want exceptions, they want diversity, they want critical thinking, but they have some guidelines how to make the composition where the individual elements have their interrelations and relations as a whole. Okay, and the idea of connecting abstract mathematical concepts to concrete ideas aims to make mathematical lectures pleasing, tangible, meaningful, and appropriate for the newest generations of students, Z and alpha generations. Z generations which were born from 95 to 2010, and after 2010 we have this alpha generations that are worse than this. Current students are Z generations, and I believe that we all strive to keep their attention and their continuous work, which is inevitable for grasping the mathematical knowledge. So they can also help to better understand both fields, mathematics and art fields, and of course inspire the students' creativity and divergent thinking, and help teachers to communicate mathematics to students actively, and maybe remove the prejudice of mathematics as a cold and austere science. That was all. Aha, okay. Did I? Yes, that was all. Thank you for your attention.
Any questions or remarks?
Okay, I have some remarks. You see, there is a famous expression by Einstein. You really understand something if you can explain this to your grandmother.
Pardon?
Наистина разбираш нещо, ако може да го обясниш на баба си. You really understand something if you are able to explain it to your grandmother.
Yes, I understand.
Also, there was some Ukrainian book with problems for the secondary school, and the idea was there are stupid problems, how to solve basins with pipes. Of course, this is quite annoying, but the same problem you can solve. A group of elephants drink water from a lake.
Oh, yes.
Any questions on
I had some experience. I had an examination at the university, and I asked the student, what is a group? Okay, a group is a set with some operations, some action, etc., etc. Okay, you have a set with two objects, an apple and a pear. The operation apple times apple is apple, apple times pear is pear, etc. Prove that this is a group. Oh, it's quite difficult. I don't know.
They cannot easily transfer from numbers to shapes. Yes. They cannot. They need some time.
Norbert Wiener wrote in his book I Am Mathematics, Beauty of Mathematics understood very many people. It's not question.
It's saying that you mentioned a book, Beauties of Mathematics.
I'm a mathematician.
Norbert Wiener wrote about it. Beauty of Mathematics understood very many people.
Yes, of course, yes.
Other questions, please.
You had these paintings and you talked about artists using the golden ratio. So do you think that they actually try to apply it, or you know whether they try to apply it, or it is because it's close to that we find the result appealing? So it's like
Escher was a good mathematician, and he was working with hyperbolic geometry and tried just to depict.
Escher, but like Da Vinci or Vermeer, which where they try. You had this with the golden ratio pictures, like in Mona Lisa.
Yes,
they were going for it.
Or after that.
I'm not sure. We find this appealing because, as you said, with the beautiful people, that the closer they are, the more beautiful we find them.
Actually, I posed that question to myself when I was checking that, whether they were before sketching the painting, whether they were paying attention on the golden spiral, or it is discovered after. I'm not sure. I don't know. I forgot to check it because I thought on that, but I didn't check it. Maybe I can find some information about that.
Okay, thank you. Other questions? If not, thanks again
Thank
for
you.